we have news from the edge of our solar system regarding the celestial body B.I. Atlas. It is no longer behaving like a typical comet. A few days ago, astronomers observed this interstellar visitor, moving within 2 astronomical units of the Sun, and beginning to brighten far beyond predictions. Its coma has swelled to half the diameter of our star. Its light has shifted to a troubling shade of green, and most bizarrely, it has formed a tail pointing directly toward the Sun, something that should be impossible, as it hurtles toward Mars at a dizzying speed. Researchers admit they cannot explain what they are witnessing. The countdown to perihelion has begun, and with each passing hour, this wandering extraterrestrial object looks less like a comet and more like a cosmic riddle demanding an answer. Stay with us until the end of this program to find out what this startling story means for everything we thought we knew, and what happens when alien chemistry finally awakens. Part 1. It is getting bigger and brighter. The numbers do not lie, even when they defy all explanation. In mid-September of 2025, astronomers tracking B.I. Atlas noticed something unsettling in the data. The brightness measurements began to climb above the predicted curves, increasing from an expected magnitude of 15 or 16 to an astonishing level of 12 to 14. For those unfamiliar with the inverse logic of astronomical magnitude, this represents a significant change. To put it simply, magnitude numbers run backward. The lower the number, the brighter the object. A drop of just 2 magnitudes means this object is now emitting 6 times more light than predicted. But this was not a gradual change. This was an acceleration. The Comet Observation Database, known as COBS, for those who track these wandering bodies in the sky, began to show data points climbing steadily above the expected standard brightening curve. For a warming comet, sky watching from Earth confirmed this trend. Comet B.I. Atlas was shining brighter than any model astronomers had built for its journey toward the Sun. The critical moment came as the object moved to within about 2 astronomical units from the Sun. In early to mid-September, for context, an astronomical unit is the distance from the Earth to our star, about 93 million miles. At 2 astronomical units, Comet Atlas was still twice as far from the Sun as we are, yet something fundamental had changed. The increase in brightness was not just unexpected, it was startling in its intensity. What could cause such a sudden increase in brightness? The most likely explanation involves volatile ices, frozen carbon dioxide, water, and other exotic compounds locked within the comet's nucleus since the object's formation around another star. As the intensity of solar radiation increases, these materials don't just melt. They transition explosively from a solid to a gaseous state, carrying dust and debris with them, and creating expanding clouds that reflect sunlight back to Earth. But here is what is concerning. Rapid brightening events often signal instability. Comets that experience sudden outgassing can break apart, creating multiple objects or spectacular clouds of debris. They can also exhaust their volatile reserves quickly, leading to an equally rapid decrease in brightness. The fact that Comet Atlas was brighter than models predicted suggests that we are witnessing processes that astronomers do not yet fully understand. This is not a cause for global panic. However, NASA has confirmed that Comet Atlas maintained a safe distance, never approaching Earth any closer than 1.8 astronomical units, nearly double our distance to the Sun. The alert is not about an impact, but about understanding. We may be witnessing an interstellar time capsule, undergoing fundamental changes in real time as it journeys toward the inner solar system. Consider the implications. This object was formed in the debris disk, around another star, perhaps hundreds of light years away. It condensed from material that had never felt the warmth of a sun, and had not experienced the particular conditions that formed the planets in our cosmic neighborhood. Yet now, for the first time in its existence, it is confronting the environment of intense radiation in the inner solar system. The surge in brightness may represent the awakening of chemical reactions that have been dormant for millions or even billions of years. Unique types of ices, stable in the deep cold of interstellar space. Could it be sublimating for the first time since this object was formed? We might be witnessing the unveiling of chemical signatures from another star system, preserved intact throughout its intergalactic journey. The element of time adds another layer of intrigue. Comet BAE Atlas is approaching a series of crucial milestones that will determine what astronomers can learn from this unprecedented visitor. October 3rd marks its closest approach to Mars, a mere 30 million kilometers away, a distance close enough for the orbiting spacecraft around the red planet to potentially observe details invisible from Earth. Towards the end of October, specifically from October 29th to 30th, the comet will reach its perihelion, its closest point to the Sun, at a distance of approximately 1.36 to 1.4 astronomical units. This is where the story takes a challenging turn for observers on Earth as the comet BAI Atlas draws near its encounter with our star. Its position in the sky moves perilously close to the brilliant glare of the Sun. From early October to early November, the comet enters a region that astronomers call superior conjunction, a period when the Sun's light makes observation nearly impossible from the Earth's surface. This means that the peak activity of this interstellar visitor, the moment when solar heating reaches maximum intensity and the comet's true nature might be revealed, will largely unfold hidden from our sight. We will be forced to rely on the mechanical eyes of spacecraft positioned throughout the solar system, especially those orbiting Mars, to witness what could be the most spectacular interstellar chemical display in human history. The brightening trend suggests that BAE Atlas will not pass its perihelion quietly. Current observations suggest an object being energized by its encounter with the Sun, possibly heading towards outburst events that could illuminate previously unseen details about its structure and composition. But will these revelations occur during the weeks when Earth's telescopes are obscured by the Sun's light? The data gathered from September observations paints a picture of an object in transition. Its measured brightness is trending above the predicted curves, showing that Comet 3I Atlas is becoming different from what it once was during its long journey through the space between the stars. The question is whether this transformation is the normal behavior of a comet from a foreign object, or if it is something entirely unprecedented in our experience with visitors from other star systems. In the next few minutes, we will explore why this object's coma is more extended than it should be, and why its tail points towards the Sun instead of away from it, and how a recent change to a strange green color might signal chemical processes never before observed in an interstellar visitor. The mysteries are mounting quickly as brightness measurements are soaring. But first, we need to understand what we are dealing with, because Comet 3I Atlas is no ordinary comet. It is the third confirmed object to arrive from another star system, and its behavior has shown that every interstellar object brings its own set of rules. Part 2. The discovery and classification of the story of Comet 3I Atlas begins on a mountaintop in Chile, where robotic eyes scan the night sky with a mechanical precision that human astronomical observers can only admire. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected a faint streak of light moving against the background stars. Initially classified as a routine minor body, this seemingly unremarkable observation would soon rewrite our understanding of visitors from between the stars. What makes an object interstellar? is not simply that it originates from outside the solar system. It is the mathematical certainty that it can never be gravitationally bound into an orbit around our sun, a trajectory so high in energy that once it completes its swing around our star, it will continue outward forever, never to return. Orbital mathematics is unforgiving in its precision, and this object has too much velocity to be captured by the sun's gravity. The designation says it all. The I for interstellar, and the number 3 indicating this is only the third such confirmed object in human history. Its two predecessors were 1I, Oumuamua in 2017 and 2 Hadze Borisov in 2019, each celestial body, surprised astronomers with their unique characteristics, making them difficult to classify. Now, Atlas continues this unpredictable pattern of interstellar objects. The discovery process reveals just how difficult they are to detect. Atlas operates from the Ricardo Observatory in the Atacama Desert, Chile, as part of a global network, designed to detect potentially hazardous asteroids approaching Earth. The system takes multiple images of the same region of the sky in a short period, then uses a computer algorithm to identify anything moving against the background of stars. On that July night, Atlas appeared as just a faint streak of light, difficult to distinguish from the thousands of asteroids, comets, and space debris that reside in the inner solar system. But pre-covery images, which are earlier photographs showing the object before its official discovery, revealed that Atlas had been hiding in astronomical databases for weeks before an AI recognized its significance. This delay in identification is common with interstellar objects, which often appear as asteroids in initial observations before developing the fuzzy clouds and tails that mark them as comet-like objects. The initial assessment showed a faint cloud surrounding the central nucleus, immediately suggesting that Atlas was not just an ordinary planetary rock. Comets develop these fuzzy atmospheres when solar heat causes ice to sublimate, creating expanding layers of gas and dust. The presence of a gaseous coma at such a great distance from the Sun, as Atlas was still more than 3 astronomical units away when discovered, indicated that the object contained volatile materials capable of outgassing even in the cold environment of the outer solar system. As news of the discovery spread through the astronomical community, larger telescopes began to turn their gaze toward this new interstellar visitor. The Hubble Space Telescope captured detailed images in July, while the Very Large Telescope in Chile and other ground-based observatories contributed their own observations. These follow-up studies revealed a much more complex object. Compared to the initial discovery images, estimates for the size of Comet Atlas remain uncertain, frustratingly so. A common problem when studying objects that are too distant and faint to measure directly. An August update from Hubble narrowed the possibilities to a nucleus with a diameter somewhere between 0.3 and 5.6 kilometers, a wide range, reflecting the difficulty of separating the solid nucleus from the gas that surrounds it. This uncertainty in size is critical because it affects calculations of the object's mass, density, and structural integrity as it approaches the Sun and its extreme temperatures. Velocity calculations further reveal the extraordinary nature of this object, which is currently hurtling through space at about 130,000 miles per hour, equivalent to about 58 kilometers per second. Comet Atlas is moving at a velocity that dwarfs any object native to the solar system. For comparison, Earth orbits the Sun at a leisurely 30 kilometers per second, and the comet's speed will continue to increase as the Sun's gravity accelerates it toward its perihelion, potentially reaching 68 kilometers per second, or over 150,000 miles per hour. These velocities underscore the exotic nature of this visitor, as no object born within the solar system could naturally achieve such speeds without the aid of gravitational flyby maneuvers. around the giant planets. Comet Atlas bears the kinematic signature of an interstellar origin, accumulated over millions of years of travel through the galaxy under the influence of stellar gravitational fields and the galaxy's own rotation. The confirmed rarity of interstellar objects makes each one invaluable to science. Before 2017, astronomers had only theoretical models to guide their understanding of how such objects might behave during their interstellar journeys. Oumuamua shattered many assumptions with its elongated shape and mysterious non-gravitational acceleration. Tusae-Borisov looked more like a comet, but it revealed a chemical composition different from anything in our solar system. Now, Comet Atlas adds a third data point to this sparse dataset, and early indications suggest it will prove to be just as unique as its predecessors. The object's behavior is challenging models in new ways, especially its unexpectedly large cometary tail and its unusual evolution in brightness. Each interstellar visitor seems to carry its own set of physical and chemical rules, suggesting the galaxy harbors a much greater diversity in the complex formation processes of small bodies than we ever imagined. The classification process is not just about confirming its interstellar status. Astronomers also have to determine if Third Eye Atlas is an asteroid, a comet, or something else entirely. The presence of a gaseous halo suggests comet-like behavior, but the specific composition of gas and dust revealed through spectral analysis will ultimately determine how this object formed and evolved in its parent star system. This is not a local comet pushed in from the cloud, a distant reservoir of icy bodies that occasionally sends visitors to the inner solar system. Third Eye Atlas formed around another star, condensing from materials that experience temperatures, pressures, and chemical environments completely different from anything originating in our cosmic neighborhood. It represents a direct sample of the planet formation process that occurred light years away, possibly billions of years ago. Orbital calculations place Third Eye Atlas on a path that will provide unprecedented observation opportunities, especially during its close approach to Mars on October 3rd. This alignment is not coincidental. The object's orbital inclination and timing coincide favorably for spacecraft observation, just as Earth-based telescopes will lose sight of it due to the sun's glare. But to understand what we are seeing, it takes more than just knowing where Third Eye Atlas came from and where it is going. But the real mystery lies in how it is behaving as it encounters our sun's radiation for the first time in its existence, and why that behavior is so markedly different from theoretical predictions. Part 3. Orbit and Timeline. Time is running out for Third Eye Atlas, and for the astronomers racing to understand it before it disappears into the sun's light. The mathematics of orbital mechanics have plotted its precise path through the inner solar system, marking the critical dates that will determine what humanity can learn from this third confirmed interstellar visitor. October 3rd, 2025, marks the first major milestone. On this day, Eye Atlas will fly past Mars at a distance of about 30 million kilometers, approximately 0.1902 astronomical units in cosmic terms. This was an extremely close encounter, bringing the visitor to Mars and into the operational range of many spacecraft orbiting the red planet. The timing could not have been luckier or more inconvenient, just as BAI Atlas reached its closest point to Mars, offering spacecraft the clearest possible view of an active interstellar object. Telescopes on Earth were beginning to lose the ability to track it, as the unforgiving geometry of orbital mechanics placed the comet ever closer to the sun's position in the sky, creating an observational challenge that would soon become insurmountable by the end of October, specifically the 29th and 30th. BAI Atlas reached perihelion, its closest approach to the sun, at about 1.36 to 1.4 astronomical units. This distance placed it just inside the average orbit of Mars, subjecting the interstellar visitor to solar radiation at an intensity it had never before experienced during its interstellar journey. This moment coincided almost perfectly with the period of most difficult observation from Earth. The change in speed tells its own fascinating story. Currently moving at tens of kilometers per second, BAI Atlas would reach its maximum velocity near perihelion, potentially up to 68 kilometers per second, or about 152,000 miles per hour. To put that into perspective, Earth maintains a stable orbit around the Sun at about 30 kilometers per second, meaning BAI Atlas would be moving more than twice as fast as our entire planet. These velocities are not just impressive statistics, they reveal the fundamental physics that govern interstellar motion, unlike objects originating from the solar system, which gain speed through gravitational interactions with the Sun and planets over billions of years. BAI Atlas carries the kinetic energy accumulated during its journey between star systems. Each kilometer per second of its velocity represents the vast distances it has traveled through interstellar space, influenced by the gravitational fields of many stars and the rotation of the galaxy itself. Its approach trajectory placed BAE Atlas near the ecliptic plane, the relatively flat disk containing most planetary orbits. This geometry facilitated the close encounter with Mars, and later allowed for a more distant encounter with Jupiter. In the year 2021, this orbital alignment was no coincidence. Objects approach from random directions in three-dimensional space. It would be unlikely to pass so conveniently close to multiple planets during its brief journey through the solar system. Safety factors were never brought into the calculation for BAI Atlas. Despite being classified as a potentially hazardous object during initial tracking, its closest approach to Earth occurred at about 1.8 astronomical units, nearly twice the distance to the Sun, and far beyond any imaginable threat. NASA confirmed this safe distance, which eliminated public concern about a collision, allowing astronomers to focus on the scientific opportunity, rather than planetary defense considerations. The real challenge lay in the geometry of observation. From early October to early November, Bialis experienced what astronomers call a conjunction, over a period, when its position in Earth's sky placed it too close to the Sun to be observed. In fact, its solar elongation, the angular distance between the comet and the Sun as seen from Earth, dropped below 30 during much of this critical phase. Imagine you are trying to spot a firefly hovering next to a searchlight, and you will begin to understand the observational predicament. Even the most sophisticated telescopes could not separate the faint light of BAI Atlas from the overwhelming glare of the Sun when the two objects appeared close together in the sky. This natural limitation of Earth-based astronomy meant the comet's most active phase could unfold, largely hidden from human view. The timing of the conjunction created a fundamental irony in the encounter with Bialis, just as the solar heat reached its maximum intensity, and the comet was likely to undergo its most dramatic transformations. The terrestrial astronomical community would be effectively blind. Peak outgassing, potential fragmentation events, and maximum tail development could all occur during the weeks when ground-based telescopes were rendered ineffective. This observational gap placed particular importance on spacecraft positioned throughout the solar system, especially those orbiting Mars. The European Space Agency with its Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, suddenly took on the role of humanity's primary eyes on one of the most significant astronomical events of the decade. The post-perihelion timeline offered both hope and reality for what observers could expect. Assuming BA Atlas survived its encounter with the Sun, for observation from Earth could potentially continue into November or early December, as the solar elongation angle increased beyond practical limits. However, the comet would likely be fading rapidly by then, having exhausted much of its volatile material during its period of peak heating, unobserved. Brightness predictions suggested that even at its brightest, Comet Atlas would remain only a telescopic object for observers on Earth. The estimated peak brightness hovered around magnitude 11 or 12, far too dim to be seen with the naked eye, but well within the reach of amateur astronomical equipment. This lack of a spectacular naked-eye display might have disappointed casual observers, but it did not diminish the scientific value of the encounter. The records reveal another crucial aspect of Comet Atlas's timeline. As the object approached perihelion, its speed continued to increase under the Sun's gravitational acceleration. However, immediately after its closest approach, that same gravitational force began to slow the comet down as it moved away from the Sun's position. This change in velocity affected the timing of its peak heating and the window of time available for observation by spacecraft at Mars. Looking beyond perihelion, orbital, calculations showed that Comet Atlas would continue its journey out of the solar system, eventually approaching Jupiter in March of 2026. And while this encounter would occur at a much greater distance than the Mars flyby, it could provide another opportunity for spacecraft observation as the comet began its final departure from the solar system. The timeline created a narrow window of opportunity unlike any astronomy had faced before, unlike periodic comets that return regularly, allowing for multiple research opportunities. Comet Atlas presented a single chance to understand an object from another star system. The observational challenges, the timing of the conjunction, and the spacecraft opportunities had to align perfectly for humanity to extract the maximum scientific value from this cosmic visitor. As the decisive October days approached, the question was not only what Comet Atlas would reveal about itself, but whether our observational capabilities would be sufficient to capture those revelations. The mathematics of orbital mechanics had set the schedule, and that schedule waited for no one. Part 4. The Cometary Coma. Its expansion and structure. The most astonishing discovery about Comet Atlas was not its interstellar origin, or its unusual orbit, but rather the immense scale of the atmosphere that it is creating around itself. In September 2025, NASA's Sparks telescope discovered something that challenged every model astronomers had ever built about the behavior of comets. A halo of carbon dioxide extended 348 kilometers from the nucleus. To understand the magnitude of this measurement, consider that this strange atmosphere stretched to about half the diameter of the Sun. The halo of comet BAE Atlas had grown large enough to contain the entire orbit of Mercury, creating a giant bubble of gas and dust that far surpassed anything ever seen around the comets. In our solar system, this was not only unusual, it was unprecedented in the history of studying comets. This gaseous layer forms when solar radiation warms. The ice locked inside the comet's nucleus, causing it to sublimate directly from a solid to a gas, without passing through a liquid state. Imagine a cosmic snowball, gently vaporizing in the sunlight. But this comparison does not quite capture the intensity of this process. As the frozen material abruptly transforms into gas, it carries dust and larger fragments outward, creating an expanding atmosphere that can grow to an enormous size. The composition of Comet BAI Atlas tells a story of its formation in conditions completely different from our own solar system. The prevalence of carbon dioxide over water vapor suggests this object condensed in a region where carbon dioxide could freeze more easily than water, perhaps in the outer reaches of another star's planetary disk, where temperatures were low enough for carbon dioxide ice to remain stable, while water existed mostly as a vapor. This carbon dioxide-rich environment hints at the chemical composition and the conditions present during the birth of comet BAE Atlas. Most comets in the solar system have water as their main volatile component, with carbon dioxide playing a lesser role. The reversed ratio, seen in BAI Atlas, suggests that the temperatures and pressures of its formation were unlike anything that the native objects in our cosmic neighborhood have experienced. However, this was not its only unusual characteristic. Images from the Hubble Space Telescope and ground-based observatories showed its structure, challenging fundamental assumptions about cometary behavior. Instead of the classic tail stretching away from the sun, Comet Atlas exhibited what astronomers call an anti-tail, a stream of material that seemingly pointed toward the sun. This sunward-pointing structure represented a puzzle that has kept researchers awake at night. Conventional cometary physics dictates that solar radiation pressure should push gas and dust away from the sun, creating the familiar tails that have inspired the human imagination for millennia. However, Atlas seemed to be violating this fundamental principle, ejecting material in directions contrary to textbook theory. Hubble observations on July 21st captured what scientists described as a forward-facing plume, a fan-shaped structure extending from the nucleus toward the sun, not away from it. Follow-up images by the Gemini South Telescope on August 27th showed that this unusual geometry persisted and evolved, demonstrating that the anti-tail represented a stable feature rather than a temporary anomaly. The physics behind anti-tail formation involves more complex processes than simple radiation pressure. Large dust particles, too massive to be easily pushed by solar photons, can maintain a sunward trajectory if they are ejected from the nucleus with a sufficient initial velocity. Additionally, projection effects can make material moving in three-dimensional space appear to point toward the sun when viewed from Earth at a specific vantage point. However, theoretical models struggle to explain the persistence and prominence of Atlas's sunward plume of material, a structure that seems too well defined and prolonged to be the result of simple projection effects, while the required dust particle sizes and ejection velocities needed to create such a large anti-tail exceed physically plausible limits for a cometary nucleus. Recent analysis suggests the anti-tail could be caused by an unusual rotational state or unique surface properties of the interstellar object. A slowly rotating nucleus could maintain a temperature differential between its day and night sides, concentrating outgassing in specific directions. Alternatively, the surface composition of Comet Atlas might consist of materials that react to solar heating in ways unfamiliar to researchers accustomed to studying local comets and the expansion speed of the surrounding coma. The comet adds another layer of mystery. Spectral observations indicate that the velocity of the gas within the comet's coma exceeds the typical values for comets at a similar distance from the sun. This enhanced outgassing could be the result of the release of hypervolatile compounds that are only stable under interstellar conditions, sublimating rapidly upon first contact with significant solar heating. The comet's temperature measurements reveal other anomalies. Temperatures recorded from infrared observations suggest heating mechanisms beyond simple solar absorption. Possible explanations include chemical reactions between compounds previously separated, or the release of energy stored in structures of exotic ice crystals that formed under interstellar conditions. The three-dimensional structure of the coma was reconstructed from various perspectives and wavelengths of light, revealing asymmetries that indicate uneven outgassing from the nucleus's surface, rather than the typically more symmetrical gas clouds of well-studied comets. Bialas displays jets and fans of material escaping from specific regions of the nucleus. These jets suggest that the nucleus surface contains distinct areas, rich in volatile materials, possibly exposed by impacts or thermal cycling during the object's interstellar journey. The outgassing pattern may hold information about the comet's formation environment and subsequent evolution over millions of years of travel through space. Analysis of the dust in the coma reveals a particle size distribution unlike that found in solar system comets. The abundance of large particles needed to produce the observed tail structure suggests that Biela's either formed with a ratio of dust to ice different from local comets, or that its dust grains underwent transformative processes during its interstellar transit. The expansion shows variations over time, correlating with the comet's distance to the Sun and possibly its rotation period. As comet Biela's continues its approach to perihelion, the coma continues to grow and evolve, likely reaching even greater sizes as solar heating intensifies. Modeling efforts to predict the future evolution of the coma face unprecedented challenges. Its unusual composition, inverted tail shape, and outgassing rates all demand adjustments to standard cometary physics models. Researchers are actively developing new theoretical frameworks. Over time, as observations continue to reveal unexpected behaviors, these implications extend far beyond Comet Atlas itself. If interstellar comets frequently exhibit such unusual coma characteristics, it suggests that our understanding of cometary physics, based primarily on objects originating from our solar system, may represent only a narrow subset of possible behaviors. Each interstellar visitor could force us to reconsider fundamental assumptions about how these objects form and evolve. As B.I. Atlas approaches its key encounters with Mars and the Sun, the continued expansion and evolving structure of its coma will provide critical tests for competing theoretical models. The question is whether the most dramatic changes will occur during the period of unobservability when Earth-based telescopes cannot track the comet's behavior. But the coma's evolution represents only one aspect of B.I. Atlas's transformation, as it is exposed to our Sun's radiation. The most visually striking and astonishing change occurred in mid-September, when the entire comet began to glow with an eerie green light, signaling a chemical reaction unlike anything ever observed in an interstellar visitor. Part 5. The green color shift in mid-September 2025. B.I. Atlas was already a source of great excitement in the astronomical community. It turned green, not gradually, not subtly, but with a vibrant green glow that transformed this interstellar visitor from a faint smudge into something that looked almost alive against the dark. Starry background. The color change was not immediately apparent to casual observers. B.I. Atlas remained too faint to be seen with the naked eye, but sensitive cameras attached to telescopes around the world began to record images revealing a green hue unmistakably surrounding the comet's nucleus. The transformation became particularly apparent in photographs taken during the lunar eclipse on September 14th, when the moon fell into shadow, creating a darker sky, increasing the contrast of the comet's nascent glow. The green light tells a story, written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet light from the Sun, their electrons jump to a higher energy state. When these electrons fall back to their ground state, they emit light at specific wavelengths that our eyes perceive as distinct colors. In the case of Comet Atlas, the green emission most likely originates from diatomic carbon, two bonded carbon atoms, commonly known as C2 in chemical notation. Diatomic carbon acts like a molecular billboard in space. When energized by the Sun's ultraviolet rays, the molecules C2 emit light at a wavelength of about 516 nanometers, creating the characteristic green glow. That made Comet Atlas one of the most visually distinctive comets observed in recent years. This emission process is known as fluorescence, turning invisible solar energy into light that is visible and can travel millions of kilometers to reach telescopes on Earth. But this is where the story becomes puzzling. Initial spectroscopic observations of Comet Atlas revealed relatively little evidence of carbon-containing compounds. The initial chemical analysis indicated a composition of mostly carbon dioxide and water vapor, with very small amounts of the carbon molecules that typically cause a comet's green color. This apparent contradiction between the observed green light and the measured chemical composition left researchers puzzling to understand what was really happening in the comet's expanding atmosphere. One possibility involves the outgassing behavior. As Atlas moved closer to the Sun and crossed the threshold of 2 astronomical units in early September, the increasing solar heat may have begun to sublimate previously inaccessible layers of carbon material inside the nucleus. These materials, locked away in the comet's core during its long interstellar journey, might now be exposed to solar radiation for the first time in their existence. The timing of the green color change curiously coincides with the brightening phase, which was rapidly observed in mid-September. This suggests that the same physical processes responsible for the sudden increase in brightness may have been the catastrophic release of volatile materials from subsurface reservoirs, which also triggered the chemical reactions that produced the green emission. Alternative explanations for the color change involve more complex chemistry than simple dicarbon. Comets can contain dozens of different carbon-containing molecules, each with its own emission characteristics. The apparent green light could be the result of a blend of emissions from multiple species, or from carbon-containing molecules characteristic of the interstellar medium, which do not exist in significant quantities in solar system comets. Instrument sensitivity and processing techniques also introduce uncertainties in the color measurements. Different telescopes use different filters and imaging systems, which can produce slightly different colors of the same object. What appears as green in one image might look more blue-green or yellow-green in another, depending on the specific wavelengths recorded and the methods used. To combine them into a color image, the evolution of the green light provides more clues about the underlying chemistry. Unlike the steady emission expected from simple molecular fluorescence, observations show that the green color varies in intensity and distribution within the coma. Some regions are more intensely green than others, indicating that the molecules containing carbon are not evenly distributed throughout the expanding gas cloud. This uneven distribution could result from discrete outgassing events, where jets of material erupt from specific locations on the nucleus, carrying different chemical compositions. Alternatively, the variations might reflect chemical processing within the coma itself, as solar ultraviolet radiation breaks down complex organic molecules into simpler fragments, which then glow at different wavelengths. The green emission also provides a diagnostic tool for understanding the physical conditions in the coma. The intensity of molecular fluorescence depends on the density of molecules, their temperature, and the intensity of solar ultraviolet radiation. By measuring the changes in the green light based on the distance from the nucleus and over time, researchers could map the three-dimensional structure of the carbon-bearing gas within the atmosphere of Comet Atlas. Temperature measurements from the green emission feature showed that the carbon-containing molecules exist in thermal equilibrium with the other gases in the coma, which suggests an efficient energy transfer between different molecular species, providing insight into the collision rates and gas dynamics within the expanding atmosphere. The green appearance of 3I Atlas adds another data point to the catalog of growing differences between objects from interstellar space and native objects in our solar system. 1I Oumuamua showed no clear signs of cometary activity and thus had no color change. 2I Borisov displayed more conventional cometary colors, mostly blue and white scattered sunlight, rather than the molecular emission lines representative of comets, the first interstellar object to develop the classic green coma that amateur astronomers associate with approaching periodic comets. However, the specific wavelengths and intensity of the green emission may be subtly different from those of familiar comets. potentially revealing the unique chemical composition of objects formed in other star systems. The timing of the color change adds to the observational urgency as 3I Atlas approaches superior conjunction and becomes unobservable from Earth in early October. The green emission might continue to evolve, or it might fade away completely. The peak intensity of the molecular fluorescence typically occurs near perihelion when solar heating is at its maximum, but this crucial phase will be largely hidden from ground-based telescopes. Spectroscopic observations are attempting to identify the specific molecules creating the emission, the green glow. However, these measurements require large telescopes and favorable observing conditions, which are becoming increasingly difficult to secure. As the comet approaches the glare of the sun, every clear night becomes precious, as astronomers race against time to document the emission before the target is lost from view. The transformation of the green light is more than just a visually striking phenomenon. It offers direct evidence that this Comet Atlas, is undergoing fundamental chemical changes upon exposure to solar radiation. The molecules now glowing in the comet's coma may have existed in an inert state, chemically for millions of years, preserved in the silent freeze of its interstellar journey. Now, for the first time since its formation, Comet Atlas is truly glowing, as solar energy activates chemical processes that have lain dormant since the comet's birth around another star. The blue glow marks the awakening of alien chemistry, the first signs of molecular activity in materials formed under conditions that may be unlike anything in our own solar system. But observing this awakening presents challenges beyond the capabilities of ground-based astronomy, challenges that will soon force researchers to rely on mechanical eyes placed throughout the solar system to continue monitoring our transformed interstellar visitor. Part 6. The unforgiving timing of cosmic observation. When it comes to Comet Atlas, just as this interstellar visitor began to reveal its most fascinating mysteries, its rapid brightening, the strange atmospheric halo, the mysterious blue glow, orbital mechanics silently stole the view from Earth-based observers at the most critical moment of its journey. Professional telescopes, equipped with the most sophisticated instruments that humanity can build, also face the same fundamental limitation as amateur astronomers. You cannot observe what lies hidden behind the sun. As Comet Atlas continued its approach to perihelion, its position in the sky from Earth moved relentlessly closer to our star, creating observational challenges that no technological advancement could overcome. The James Webb Space Telescope managed to capture a spectrum of Comet Atlas on August 6th using its near-infrared spectrograph, providing crucial chemical data during one of the few windows of time when the world's most advanced observatory could safely point towards the comet without risking damage from the sun. These observations represent some of the most detailed chemical analyses were conducted on an interstellar object, but they occurred before the significant changes. In mid-September, when Comet Atlas transitioned from a merely unusual comet to a comet that was truly baffling to space telescopes, Hubble made its own contributions with observations on July 21st, capturing high-resolution images that showed a fan-like structure pointing toward the sun and set a size limit for the comet's nucleus. However, since August, new high-resolution images from major space observatories have become scarce. The observatories capable of providing the detailed analysis needed to understand the unusual behavior of Comet Atlas were also the instruments most vulnerable to the sun as the comet approached. Challenging observations from the ground. Ground-based observatories also face their own set of problems. Different telescopes use different filter systems and calibration procedures, leading to brightness measurements that do not always align. This inconsistency reflects the inherent challenges in photometry, where measuring brightness requires careful attention to conditions, atmospheric conditions, instrument calibration, and standardization procedures that can vary between observatories. Observational databases. For comets, attempt to reconcile these differences by collecting 10 brightness reports from observers worldwide and comparing them with theoretical models. Throughout September, the data clearly showed that Comet Atlas was brightening more than predicted, with its measured magnitude consistently brighter than the projected curve. But the scatter in the individual measurements reflected the challenges that observers faced when trying to track a rapidly changing object, causing their careful models to deviate. The role of amateur astronomers. Amateur astronomers, often working with smaller telescopes and less sophisticated equipment, contribute valuable long-term monitoring data that professional observatories cannot always provide. However, their measurements face additional uncertainties from atmospheric turbulence, light pollution, and equipment limitations, resulting in a combined set of observations painted a picture of unusual behavior, yet individually, they contained enough uncertainty to spark debates about what was truly happening. The solar elongation limit. The solar elongation, the angular distance between Comet Atlas and the Sun as seen from Earth, represented a fundamental limit, restricting all observations when this angle dropped below 30 degrees. Even the most powerful telescopes struggled to separate the comet's faint light from the scattered sunlight in Earth's atmosphere. Professional observatories typically cease observations when the elongation falls below 20 degrees, while amateur observers might lose track of the object even sooner, due to equipment limitations and local viewing conditions. The elongation timeline created a countdown clock that no human technology could extend. In early October, Comet Atlas dipped below the 30-degree threshold, marking the beginning of significant observational difficulties. By mid-October, the elongation had dropped below 20 degrees, effectively ending conventional observations from Earth's surface. The period of invisibility. This period of invisibility lasted until early November, encompassing the critical weeks when solar heating reached its maximum intensity. The irony was palpable, as we were trying to observe a cosmic firefly hovering next to a searchlight, using instruments designed to detect the faintest glimmers from distant galaxies, even adaptive optics systems, which can compensate for atmospheric turbulence, and coronagraphs designed to block starlight, could not overcome the fundamental physics of scattered sunlight when the comet appeared, so close to the sun's position in the sky. Limitations of space observatories. Space-based observatories, in theory, have an advantage over ground-based telescopes in dealing with solar glare, but they face their own limitations. Instruments like Hubble and James Webb have protection systems that prevent them from pointing too close to the sun, automatically shutting down observations when the solar angle becomes dangerous. These safety systems, essential for preventing catastrophic damage to billion-dollar instruments, also create an observational gap at precisely the time when they would be most valuable. The timing of Comet Atlas's conjunction cycle could not have been worse for understanding its peak activity. Theoretical models predicted that maximum outgassing and potential fragmentation events could occur, and the most impressive tail development would take place near perihelion in late October. These are precisely the phenomena that could reveal the most about the composition, structure, and origin of Comet Atlas, and they would occur largely hidden from human observation. The challenge of data processing. The challenge of data processing further complicated the observational difficulties. Images of Comet Atlas had to be carefully processed to separate the comet's signal from background stars, cosmic rays, and instrumental artifacts as the object became fainter than the sky's brightness. During the approach to conjunction, these processing steps became increasingly crucial and more prone to error. Spectroscopic observations are essential for understanding the chemical composition of the comet's coma and tail. requiring more specialized conditions than simple brightness measurements. The instruments needed to disperse the comet's light into its constituent wavelengths work best on bright targets observed against a dark sky. As Comet Atlas faded into the solar glare, the opportunity for detailed spectral analysis vanished just as chemical activity was likely peaking. Atmospheric effects. The atmospheric limitations affect different wavelengths of light in different ways. Ultraviolet emissions are crucial for detecting many molecular species in the cometary atmosphere. They become particularly difficult to observe as elongation decreases, because Earth's atmosphere scatters blue and ultraviolet light more effectively than red wavelengths. This scattering effect is what makes the sky appear blue and creates additional challenges for studying the chemical processes occurring in the expanding atmosphere of Comet Atlas. International coordination. Coordination among observatories becomes essential as viewing conditions worsen, with facilities at different latitudes and in different time zones, having to work together to maximize the limited observing time available each night. Observatories in the southern hemisphere could maintain a better view for longer than those in the northern hemisphere, creating an opportunity for extended monitoring that required careful international coordination, fluctuations in measurements. The scatter and brightness measurements reflects more than just instrumental limitations. It can also indicate real variations in the activity of Comet Atlas. Comets can experience rapid changes in brightness due to outgassing events, rotational effects, or structural changes in the nucleus. Distinguishing between measurement uncertainty and the comet's actual variability becomes increasingly difficult, as the signal-to-noise ratio decreases during the approach to conjunction. Weather adds another layer of uncertainty to ground-based observations. Cloud cover, atmospheric turbulence, and seasonal weather patterns at major observatories can eliminate crucial observation opportunities, which will never be repeated. Unlike periodic comets that return on schedule, Comet Atlas offered only a single pass through the inner solar system, making each night of observation precious and irreplaceable. In interpreting the data, the challenge extended beyond individual observations to the larger question of how to interpret the available data. The brightness trend suggested that Comet Atlas was exceeding its predicted values, which could indicate an increase in outgassing, structural changes, or simply systemic errors in the theoretical models used for comparison. Answering these questions required the kind of detailed, long-term monitoring that became impossible as the comet disappeared into the sun's glare. As Earth-based astronomy reached its limits in observing Comet Atlas, the responsibility for continuous monitoring shifted to the robotic eyes placed throughout the solar system. Spacecraft orbiting Mars, designed for entirely different missions, suddenly found themselves serving as humanity's primary observatories for one of the most significant astronomical events of the decade. Part 7. The growing concern in the astronomical community. Behind the measured language of scientific papers and carefully worded statements in astronomical bulletins, there was something akin to excitement and, frankly, a bit of concern that was spreading through the global community of comet researchers. Comet Atlas was not behaving according to the script written by decades of cometary science, and astronomers were beginning to admit, in the cautious way that scientists acknowledge uncertainty, that they might be witnessing something for which there was no precedent. The brightness trend, recorded by observers around the world, represented more than just statistical noise or measurement error. Multiple independent tracking systems, from comet observation databases to specialized amateur networks, all showed the same concerning pattern. Comet Atlas was consistently brighter than predicted by standard cometary models. This level of deviation, several magnitudes brighter than the expected value, far exceeded the limits typically attributed to observational uncertainty. The expert's perspective. Dr. Matthew Knight, a cometary scientist who has spent his career studying how these objects behave, recently noted in an interview that the rapid brightening event observed in mid-September challenged fundamental assumptions about the mechanisms of volatile release in comets. He suggested that this rate of change indicates processes are at play on much faster timescales than the gradual heating models commonly used to predict cometary behavior. Scientific excitement. This scientific uncertainty generates a special kind of excitement within the research community. The realization that they might be observing phenomena that will require new theoretical frameworks to understand. Sky and telescopes reporting on Comet Atlas reflects this tension, describing observations that continue to surprise researchers, while also acknowledging that much of what seems unusual may reflect the inherent unpredictability of objects formed in other star systems. The mysterious anti-tail phenomenon, a fan-like structure pointing toward the sun, presented its own kind of scientific puzzle. Anti-tails are not unknown in cometary science, but the persistence and prominence of the stream of material pointing forward from Comet Atlas push the boundaries of what models could readily explain. Researchers found themselves proposing scenarios of increasing strangeness, unusual dust grain compositions, irregular rotation of the nucleus, and exotic volatile mixtures to explain the behavior that defied textbook explanations and its unusual level of activity. What everyone in the field agrees on is that Atlas is exhibiting a heightened level of activity compared to typical comets at a similar distance from the sun. The coma, primarily carbon dioxide, was detected by spectroscopic instruments, extending to unprecedented distances, indicating an outgassing rate that significantly exceeds standard predictions. This is not a minor deviation from theory, but a major discrepancy that demands an explanation. The scientific community is also grappling with what researchers call outburst bias, the tendency of comets to experience brief periods of enhanced activity, which can create the false impression of sustained, unusual behavior. Comets are notoriously prone to sudden brightenings, followed by a rapid return to predicted levels. The haunting question for observations of Atlas is whether the brightening in September was a genuine departure from normal behavior, or simply a temporary outburst that would fade as quickly as it appeared. The troubling observation gap. This uncertainty becomes more troubling when considered in the context of the approaching observation gap, the most critical period for understanding the true nature of Atlas, the weeks surrounding its perihelion, when solar heating is at its maximum intensity, will occur largely hidden from Earth-based telescopes. If the comet undergoes its most dramatic transformations during this period, researchers may never fully understand what they witnessed in September. Dr. Carijo, a researcher of interstellar objects at the European Southern Observatory, expressed the frustration of many researchers. The very moment when Atlas could reveal its most important secrets coincides with the period when Earth-based astronomy is least able to observe it. This timing represents what she calls a cosmic conspiracy against scientific understanding. The mysterious chemical composition. The debates extend beyond mere brightness measurements to fundamental questions about what Atlas represents as a physical object, its chemical composition, revealed through spectroscopic analysis, shows a ratio of carbon dioxide to water vapor that is different from what is typical for comets in our solar system. This difference could indicate the conditions formed in a completely different environment, or it may reflect chemical processing that has occurred during millions of years of interstellar travel. The contribution of the amateur community, the amateur astronomy community, became an important contributor to the monitoring effort of Comet Atlas, providing continuous observations that professional observatories could not always maintain. However, the distributed nature of amateur measurements presented its own complexities. Different observers used different equipment and processing techniques, sometimes reporting significantly mismatched brightness values, which made it difficult to determine whether the observed variations represented real changes in the comet or were simply measurement errors. Professional monitoring efforts, with tracking coordinated by the European Space Agency through its Space Situational Awareness Program, attempted to reconcile these measurement discrepancies while maintaining continuous monitoring of Comet Atlas's trajectory and brightness evolution. Their analysis confirmed the general trend of enhanced brightness, but acknowledged the difficulties in precisely quantifying the extent to which the comet exceeded theoretical predictions. The reaction in the scientific community, reflected across social networks, showed a mixture of scientific excitement and professional caution, characteristic of the response to Comet Atlas. Researchers shared preliminary images and brightness measurements, while carefully noting the uncertainties and limitations in their data. The tone suggested that scientists were aware that they were potentially witnessing something significant, while still maintaining professional skepticism about drawing hasty conclusions. The phenomenon of the blue color change. The blue color change, noted in mid-September, added another layer to the scientific intrigue. Although diatomic carbon emission could explain the observed color, the timing and intensity of the blue glow did not perfectly match the chemical composition, indicated by previous spectral observation data. This apparent discrepancy between what researchers were measuring chemically and what they were observing visually suggested either limitations in the measurements or more complex chemical processes than standard models predicted. The findings were discussed in academic conferences and scholarly discussions, was scheduled for the meeting of the American Astronomical Society's Division for Planetary Sciences, including many talks focused on observations of Atlas and efforts in theoretical modeling. The abstracts showed that research groups around the world were trying to understand not only what Comet Atlas was doing, but also why existing models could not accurately predict its behavior. The sense of urgency in the research, this feeling of urgency among researchers, reflected more than scientific curiosity. It represented the realization that opportunities to study interstellar objects remain extremely rare, with only 3 confirmed interstellar objects in human history, each one providing data that is irreplaceable about the conditions in other star systems and the processes that govern the formation of small bodies throughout the galaxy. International collaboration intensified. This international cooperation strengthened as the observation window narrowed, with telescopes in Chile, Hawaii, the Canary Islands, and Australia coordinating observations to maximize coverage. As Comet Atlas approached its solar conjunction, which would end routine tracking from Earth, each facility contributed unique capabilities from high-resolution imaging to specialized spectroscopic instruments in an effort to extract scientific value to the fullest from the remaining observation opportunity. The Public Communication Challenge. The professional astronomical community also faced challenges in communicating with the public about Comet Atlas. Media reports sometimes exaggerated the certainty of scientific conclusions or sensationalized aspects of the comet's behavior, which researchers themselves admitted were uncertain, balancing public excitement about the interstellar visitor with the inherent uncertainties of ongoing research required careful attention to how findings were presented and explained. Implications for risk assessment. Risk assessment models developed for asteroids that are potentially hazardous received new attention in the context of Atlas, not because the comet posed any danger to Earth, but because of its unpredictable behavior, highlighting the limitations in our current understanding of how small bodies behave under the influence of heat from the sun. If researchers cannot accurately predict the behavior of Comet Atlas, then questions arise about the reliability of the models used to assess the risk from other objects. The excitement generated around Atlas reflects the nature of scientific discovery, the realization that nature always creates phenomena that are more complex and surprising than human theories predict. As October approaches and observations from Earth become increasingly difficult, Astronomers hope that spacecraft positioned throughout the solar system can capture the discoveries that ground-based telescopes will be forced to miss. Part 8, Comet C, 2023. A3. Atlas flies by Mars. A golden opportunity, while Earth prepares to lose sight of Comet C, 2023. A3 Atlas in the sun's bright glare. Another world is positioning itself for a front-row seat to witness one of the most significant astronomical events in recent memory. On October 3, 2025, Mars will be the site of humanity's closest encounter with this interstellar visitor, offering the spacecraft orbiting the red planet unprecedented opportunities to observe C 2023 A3 Atlas from a vantage point that telescopes on Earth can only dream of reaching. The geometry could not be more favorable, as C 2023 A3 Atlas sweeps past Mars at a distance of about 30 million kilometers, equivalent to about 0.2 astronomical units. Several spacecraft currently active in orbit around Mars will have the opportunity to point their instruments toward this cosmic visitor. This timing places the observations just a few days before the superior conjunction occurs, making tracking from Earth impossible, creating a crucial handover from ground-based to space-based monitoring. The spacecraft ready to observe include the European Space Agency's Mars Express, launched in 2003, and still operating well beyond its originally planned mission duration, carrying the high-resolution stereo camera HRSC, which has mapped the Martian terrain in detail, unprecedented in more than 20 years. Despite being designed for planetary geology research, HSC possesses the sensitivity and resolution that may be necessary to capture detailed images of the nucleus and inner coma structure of C 2022 E3 Atlas. Dr. Colin Wilson, the project scientist for the ExoMars Trace Gas Orbiter, has confirmed that mission planners are evaluating opportunities for both the color and stereo imaging system known as KSS and the Nomad Occultation Spectrometer to observe the interstellar visitor. These instruments were designed to study the atmospheric composition and surface of Mars, and may have the capability to detect chemical signatures. For a more extensive mapping of the comet, NASA's Mars Reconnaissance Orbiter presents perhaps the most compelling possibilities for detailed observation, with its high-resolution imaging, science experiment, or HiRISE, which regularly captures surface details smaller than 1 meter from its orbital altitude of about 300 kilometers above Mars, while CU-2 E3 Atlas will be much farther away. The superior resolution of HiRISE could resolve structural details of the comet's nucleus, which remain invisible to Earth-based telescopes. The MAVEN spacecraft, NASA's Mars Atmosphere and Volatile Evolution mission, carries spectroscopy instruments specifically designed to analyze atmospheric composition and dynamics. These capabilities could prove valuable in studying the chemical composition of C 2022 E3 Atlas, particularly the carbon dioxide-rich gases that dominate its spectral signature. However, these observation opportunities come with significant technical challenges. All of the Mars orbiters were designed and optimized to study the red planet, and not to track fast-moving objects against a background of stars. The spacecraft's guidance systems were developed for observing a large, nearby planet, and must be reconfigured to track a small, distant target moving at interstellar velocity. Signal strength presents the most fundamental limitation, even at its closest approach to Mars. C 2022 E3 Atlas will appear extremely faint to the spacecraft's instruments, which were designed to observe planets rather than deep space. The comet's brightness is estimated to be between magnitude 10 and 24, even during its brightening phase, pushing the detection limits of most cameras and spectrometers in orbit around Mars. Dr. Wilson has acknowledged these limitations in recent communications with the international astronomical community, noting that while observing C-2023A3 Atlas from Mars is theoretically possible, the actual scientific benefit depends on several factors, including the comet's brightness at its closest approach, atmospheric conditions on Mars, and the specific geometric alignments required to successfully leverage the observational advantage from Mars. The advantage of observing from Mars extends beyond mere proximity. The viewing geometry from Mars during the October 3rd flyby offers a perspective on C-2023A3 Atlas that is not visible from Earth. The solar phase angle, the angle between the Sun, the comet, and the observer, will differ significantly between the perspectives of Mars and Earth, potentially revealing details about the cometary atmosphere structure, and tail morphology obscured from ground-based telescopes. Solar-wind interaction is another area where Martian orbiters can contribute unique observations. The collision of C-2023A3 Atlas with the solar wind, a stream of charged particles flowing from the Sun, could produce phenomena that are detectable by the plasma instruments and magnetometers carried by some Mars missions. These interactions could reveal information about the comet's internal structure and composition through changes in its magnetic and electrical properties. International coordination, the coordinated efforts of the European Space Agency for the Mars flyby observations involve an unprecedented collaboration between missions, designed for entirely different scientific purposes. Mars Express, originally planned for surface geology and atmospheric studies, now finds itself repurposed as an interstellar celestial observatory. Trace Gas Orbiter, focused on detecting methane and atmospheric chemistry, must adapt its instruments for cometary spectroscopy. Timing constraints add another layer of complexity to the planning for the Martian orbiter observations, adhering to pre-established schedules for routine planetary observations, communication windows with Earth and spacecraft maintenance activities, incorporating observations of C-2023A3 Atlas into these schedules required careful coordination to avoid conflicts with primary mission objectives, while also maximizing scientific opportunities. The data transmission challenge was also significant. Mars orbiters typically communicate with Earth during specific windows when the orbits of both planets provide favorable geometry for radio signal transmission. The images and spectra of C-2023A3 Atlas had to compete with regular planetary science data for limited communication bandwidth, potentially delaying the release of observations by several weeks or months. Ground support for the Mars orbiter observations required coordination among multiple space agencies and research institutions across the globe. The European Space Operations Center in Germany, NASA's Jet Propulsion Laboratory in California, and other facilities had to coordinate to plan observation sequences, process incoming data, and distribute the results to the international scientific community. Potential scientific value. The scientific value of successful observations from Mars could prove to be groundbreaking in understanding C-2023A3 Atlas. High-resolution images could determine the size and shape of the nucleus with unprecedented accuracy, resolving debates about the size and physical structure of the comet. Spectral observations could detect molecules invisible to Earth-based telescopes, revealing its chemical composition and preserving information about the environment where the comet formed. The structural details of the dust coma and tail, especially the unusual stream of material pointing toward the Sun that has puzzled researchers, could become clearer. When observed from the unique perspective of Mars, different solar phases could shed light on whether the anti-tail structure is a result of material being actually ejected toward the Sun, as seen from different perspectives. Managing expectations realistically required being clear about what the Mars orbiters could achieve, even under optimal conditions. The scientific results obtained from these observations may only consist of a few images and spectra, rather than comprehensive monitoring campaigns from the instruments. They were never designed for this type of observation, and their capabilities may prove insufficient to answer fundamental questions about the nature and behavior of C2023A3 Atlas. Success depends on variables beyond human control. If C2023A3 Atlas experiences another brightening event before the 3rd of October, it might become detectable by the orbiting instruments of Mars, which would otherwise find it too faint to observe. Conversely, if the comet fades from its current enhanced brightness, even the most optimistic plans may fail to capture useful data. The Mars flyby represents humanity's best opportunity to monitor C2023 A3 Atlas during crucial weeks, when Earth-based telescopes lose track of this interstellar visitor, as ground-based astronomy prepares for a hiatus that will last until early November. The robotic eyes orbiting Mars offer the only hope of witnessing the most dramatic phase of C2023A3 Atlas's encounter with our solar system. Whether these observations succeed or fail, they mark a new chapter in how humanity studies visitors from other star systems, demonstrating our growing ability to coordinate observations across multiple worlds, even as the objects of our attention zip past at interstellar velocities. Part 9. Superior Conjunction and the Disappearance. The mathematics of celestial mechanics are utterly indifferent to human curiosity. As October progresses and CT2023A3 Atlas continues its relentless journey toward the Sun, the geometric realities of orbital motion conspire to steal away our interstellar visitor, just when it might reveal its deepest secrets. Superior Conjunction. The period when C2023A3 Atlas appears too close to the Sun's position in the sky for practical observation, turns one of the most significant astronomical events in recent memory into a cosmic vanishing act. The timeline is unforgiving. It unfolds with relentless precision. In early October, C2023A3 Atlas dipped below 30 degrees of solar elongation, the threshold where significant observational difficulties begin. For ground-based telescopes, the scattering of sunlight in the atmosphere creates a bright sky background that obscures the faint signal from our interstellar visitor. Professional observatories with sophisticated equipment, telescopes with adaptive optics, and powerful light-gathering capabilities could extend observations a little longer than amateur telescopes, but even they faced increasingly challenging conditions. By mid-October, the elongation had dropped below 20 degrees, effectively ending routine observations from Earth's surface. The comet did not vanish suddenly. It faded into the sun's glare like a star at dawn, becoming progressively harder to detect until observation became impossible, rather than just difficult. This gradual transition makes it difficult to pinpoint exactly when Earth lost sight of C2023A3 Atlas, but the practical result was the same. Our primary window for observing the comet's behavior closed, just as solar thermal intensity reached its maximum, a critical phase hidden from view. The conjunction period lasted until early November, spanning about 4 to 5 weeks, when CIS2023A3 Atlas was truly invisible from Earth. This was not just an inconvenient gap in observation. It represented a complete loss of the ability to monitor our comet during the period that theoretical models predicted would be its most active phase: peak outgassing, maximum tail development, possible fragmentation events, and other significant phenomena could all occur, hidden from human sight. The profound irony becomes even clearer when considering the context of C2023A3 Atlas's recent behavior. The rapid brightening observed in September, the unusual anti-tail structure, and its characteristic green color all suggested an object undergoing fundamental changes, as it was exposed to solar radiation. Logic suggested that these transformations would intensify as solar heating increased, potentially reaching remarkable levels, near perihelion at the end of October. However, the perihelion occurs almost exactly in the middle of the synodic period, when c. 2023 Atlas appears closest to the Sun in our sky, making observation extremely difficult. The fundamental physical limitations behind this conjunction are not related to any conspiracy against scientific discovery, but are simply a geometric consequence of observing from a planet orbiting the same star as our target. As comet c. 2023 Atlas approaches perihelion, its apparent position in the sky necessarily moves closer to the Sun's position, its angular distance steadily decreasing until the comet appears to pass behind our star, creating observational conditions that no amount of technological sophistication can overcome. Professional astronomers frustratingly encounter this limitation on a regular basis when studying objects that approach the Sun's position. Solar observing satellites, like the Solar and Heliospheric Observatory, SOHO, can sometimes track comets during periods of conjunction by using coronagraphs, which block the Sun's direct light. However, the orbit of c. 2023 Atlas does not pass close enough to the Sun for these specialized instruments to detect it, which typically observe objects within a few solar radii from our star. For the scientific community, the conjunction gap creates unprecedented challenges, which is accustomed to the capability of continuous monitoring. Modern astronomy relies heavily on long-term observation campaigns, tracking objects through their entire cycles of activity. Comets, in particular, require extended monitoring to differentiate between temporary outburst events and sustained behavioral changes. The mandatory pause in observation during the most critical phase of c. 2023 Atlas eliminates the possibility of performing this type of comprehensive analysis. Limited alternatives involve positioned spacecraft across the solar system offer limited alternatives to ground-based observations, but their capabilities remain constrained by original mission designs focused on planetary rather than cometary science. The European Space Agency's Bepi Colombo is currently en route to Mercury, following a trajectory that might offer occasional opportunities to observe c. 2023 A3 Atlas from a different perspective than Earth. Yet, the spacecraft's instruments are optimized for studying Mercury, and the geometry required for comet observation may not align with the mission's operational constraints. NASA's Parker Solar Probe, designed to study the solar corona and solar wind, operates in the inner solar system, where it could theoretically encounter the tail or material of c. 2023 A3 Atlas. However, the probe's highly elliptical orbit and focus on the Sun rather than cometary phenomena limit its utility for systematic comet observation. Modeling challenges. The conjunction period also poses a challenge for theoretical modeling efforts aimed at predicting the behavior of c. 2023 A3 Atlas. Computer simulations of cometary activity rely on observational data to calibrate their predictions and validate their accuracy. The 4 to 5 week observational gap removes the very data points that modelers need to refine their understanding of how this interstellar object responds to solar heating. Uncertainty upon re-emergence, when Earth-based observations resume in November or early December 2023. A3 Atlas will likely have changed significantly from the object astronomers studied. In September, the comet may have brightened further, possibly developing a spectacular tail structure visible through amateur telescopes. Alternatively, It could have faded considerably if its volatile materials were depleted during its unobserved perihelion passage. More dramatically, a 2023 A3 atlas might have fragmented into multiple pieces during its closest approach to the Sun. Cometary fragmentation is not uncommon near perihelion, where tidal forces and thermal stress can overcome the weak gravitational forces, holding the nucleus together. If fragmentation occurred during conjunction, Earth-based observers would face the difficult task of identifying and tracking multiple objects once observation becomes possible again. The challenge of resuming observations. Resuming observations in late November or December will require careful planning and coordination among observatories worldwide. C2023 A3 atlas will emerge from conjunction in a different region of the sky, requiring telescopes to locate and reacquire the comet after weeks of invisibility. The object's brightness, position, and shape may have changed enough to make identification and tracking challenging. Impact on public and education. Public interest in C2023. A3 atlas faces its own challenges related to the conjunction. Media coverage of astronomical events often relies on dramatic images and continuous updates to maintain audience engagement. The forced silence during the conjunction period removes the steady stream of new observations, sustaining public attention, potentially diminishing interest just as the comet undergoes its most significant transformations. Educational opportunities are also affected. During this time, schools and amateur astronomy groups often use bright comets as tools to teach about solar system dynamics and observational techniques. The disappearance of C2023 A3 atlas into the Sun's glare removes these opportunities during what might be the comet's most photogenic phase, when its developing tail and nuclear activity could provide the most spectacular visual educational content. A lesson in astronomical limits. The conjunction period serves as a reminder of the fundamental limitations of astronomy, despite centuries of technological progress. Humans remain tied to their home planet for most astronomical observations, subject to the geometric constraints imposed by Earth's position relative to observed objects and the Sun. Even our most sophisticated space telescopes cannot completely overcome these limitations when objects approach too close to the position of our star. In conclusion, waiting in the darkness as C2023 A3 atlas disappears into the Sun's glare. The astronomical community prepares for a period of speculation and theoretical modeling based on incomplete data. The question is not whether the comet will change during its concealment, but what those changes will be, whether those changes will be understandable when observations resume, or if the gap will leave permanent mysteries about what occurred during the most critical phase of the encounter between this interstellar visitor and our solar system. Only time and the eventual reemergence of C2023 A3 atlas from the Sun's glare can answer these questions. Until then, we can only wait, plan, and hope that this special visitor from the distant stars will have remarkable stories to tell when it finally escapes the brilliant embrace of our star. Part 10. Perihelion Expectations. Deep within the Sun's blinding glare, rendered invisible to Earth-based telescopes, Comet A3 Atlas is preparing for its rendezvous with destiny on the 29th and 30th of October, 2025. This interstellar wanderer will reach perihelion, its closest approach to the Sun at about 1.36 to 1.4 astronomical units. Hidden from human observation, the comet will experience an intensity of solar radiation unlike anything in its millions of years of existence. During its interstellar journey, this object is likely to undergo transformations that could redefine our understanding of interstellar bodies. The evolution of its speed tells a story of cosmic violence, now hurtling through space at a speed of tens of kilometers per second. A 3 Atlas will reach its maximum velocity near perihelion, potentially reaching 68 kilometers per second, or approximately 244,630 kilometers per hour. To visualize this extraordinary speed, consider that Earth maintains a stable orbit around the Sun at a speed of about 30 kilometers per second. A 3 Atlas will be moving more than twice as fast as our entire planet, carrying the kinetic energy accumulated throughout its epic journey across the galaxy. Physics predicts that perihelion will trigger the most dramatic phase of a 3 Atlas's solar system encounter. As the Sun's heat reaches its maximum intensity, the temperature of the comet's nucleus will soar, potentially activating volatile compounds that have been stable throughout its interstellar journey: water ice, carbon dioxide, carbon monoxide, and many more exotic frozen gases could all begin to sublimate simultaneously, creating an outburst in the coma that could dwarf the unprecedented sizes observed in September. The increase in outgassing could create spectacular dust jets erupting from distinct locations on the nucleus's surface. These jets, formed as subsurface volatiles find an escape route, can create fountain-like structures, stretching for thousands of kilometers into space. The anti-tail that has puzzled observers could grow significantly, or entirely new tail structures might appear as different volatile compounds begin to contribute to the coma for the first time. Theoretical modeling suggests that the carbon dioxide-rich composition of A3 Atlas could produce unusual perihelion behavior compared to typical solar system comets. Carbon dioxide sublimates more easily than water ice at the expected temperatures near perihelion, potentially creating a gas production rate that exceeds that of primarily water-based comets by significant factors. This enhanced activity could manifest as rapid changes in brightness, coma size, and tail structure occurring over periods of hours, rather than the days or weeks typically associated with cometary evolution. The possibility of fragmentation looms over perihelion predictions like a shadow of uncertainty. Comets represent some of the most fragile objects in the solar system, held together by weak gravitational forces and the structural integrity of their icy matrices. Thermal stress caused by the intense heat from the Sun, combined with the mechanical forces generated by explosive outgassing, could overcome these binding forces and tear the nucleus apart. Fragmentation events can occur with astonishing suddenness. A comet might appear stable as it approaches perihelion, could shatter into many pieces within hours, as temperature differences create structural weaknesses, or high-pressure gas jets excavate material from within the nucleus. If Atlas were to fragment, observers on Earth would face the complex task of identifying and tracking multiple objects. As observations continued into November, historical precedents for cometary fragmentation near perihelion include spectacular examples, such as Comet Shoemaker-Levy 9, which broke apart under Jupiter's tidal forces before colliding with the planet in 1994. More recently, several comets disintegrated during a very close approach to the Sun in 2013, creating a rapidly dispersing cloud of debris as it moved away from perihelion. However, fragmentation is not inevitable, and the structural integrity of Atlas depends on factors including its nucleus composition, internal porosity, rotation rate, and the specific thermal stresses generated by its unique mixture of volatile substances. Interstellar objects may possess significantly different structural properties compared to solar system comets, potentially making them less susceptible, or more susceptible to thermal disruption. The speed at which Atlas passes through perihelion also influences the risk of fragmentation. as, unlike some comets, that linger near their closest approach. Atlas will pass through perihelion relatively quickly due to its hyperbolic orbit. This rapid passage limits the duration of peak heating, potentially reducing the cumulative thermal stress experienced by the nucleus. If Atlas survives perihelion intact, the post-perihelion phase will reveal an object transformed by its encounter with intense solar radiation. The coma could expand to even greater dimensions. As peak gas production rates distribute material over an unprecedented volume of space, new chemical species released from subsurface layers due to deep heating might appear in spectroscopic observations for the first time, with colors beyond the already observed green emissions, possibly changing as different molecular species begin to fluoresce under solar ultraviolet radiation, and complex organic compounds, if present in the nucleus, could break down into simpler fragments that emit light at characteristic wavelengths, potentially creating a rainbow of emissions across the visible spectrum. The anti-tail phenomenon that has characterized observations of Atlas could change dramatically near perihelion, as an increase in dust might generate multiple tail structures pointing in different directions, as particles of different sizes respond differently to solar radiation pressure. And the resulting morphology could provide crucial information about the nucleus's rotation rate, surface composition, and internal structure. Dust grain analysis becomes particularly important during the perihelion period, as the size, distribution, and composition of the particles ejected from the nucleus reflect the internal structure and formation conditions of the original body. Large grains might indicate a nucleus that is loosely aggregated with significant voids, while fine dust could suggest a more compact structure or specific chemical compositions that favor the creation of small particles. The magnetic and plasma environment near perihelion adds another layer of complexity to Atlas's behavior. As the solar wind, charged particles streaming from the sun, interacts with the ionized gases in the comet's atmosphere to create complex electromagnetic phenomena. These interactions can accelerate particles to high velocities, generate visible light within the coma, and influence the development of plasma tails, stretching for millions of kilometers behind the nucleus. Temperature measurements during the perihelion passage, if obtainable through spacecraft observations, could provide fundamental insights into the thermal and internal structure of Atlas. Different volatile compounds sublimate at specific temperatures, creating a chemical thermometer that reveals how solar radiation heating penetrates the surface layers of the nucleus. The aftermath of perihelion will depend heavily on the amount of volatile material that Atlas contains and how efficiently that material can escape through the nuclear surface. Objects containing large reservoirs of volatiles may continue to show enhanced activity for several weeks or months after perihelion, while those with limited volatile content may fade rapidly as their surface layers become depleted. Gravitational perturbations from the Sun's strong gravitational field near perihelion could also affect Atlas's future trajectory, while the comet will certainly continue outward on its hyperbolic path. Small changes in velocity could alter the timing and geometry of future encounters with the outer solar system planets, especially Jupiter in 2026. The perihelion represents the culmination of BY Atlas's solar system encounter, the moment when billions of years of interstellar evolution meet the high-intensity radiation environment around our star. Will this encounter produce spectacular cosmic fireworks or silent structural transformations hidden within an expanding tail? The perihelion will fundamentally change by Atlas, from the object that entered our solar system into something new and unprecedented. The question that will haunt astronomers throughout the conjunction period is whether BY Atlas will emerge from its hidden perihelion, recognizable as the same object that captivated observers in September, or as something completely transformed. by its encounter with our sun's most intense radiation. The answer lies hidden in the sun's glare, waiting for the patient geometry of orbital mechanics to reveal what perihelion has brought. Part 11. To understand the significance of Boii Atlas and its strange behavior, we must compare it with past interstellar objects. We must look back at the brief but revolutionary history of confirmed interstellar visitors. Only 2 objects before Boii Atlas, our current visitor, have been identified as definitively coming from beyond our solar system, and each has rewritten astronomy textbooks in its own unique way. The story they tell together is one of cosmic diversity, challenging all assumptions about how these messengers from other star systems should behave. Oumuamua, the first to arrive, was discovered on October 19, 2017 by the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii, initially classified as an asteroid due to its lack of a visible coma. Oumuamua soon proved that interstellar objects would not conform to earthly expectations. Its highly elongated shape, about 400 meters long and 40 meters wide, was unlike any asteroid or comet ever observed in our solar system, even more mysteriously. Oumuamua exhibited non-gravitational acceleration as it moved away from the sun, accelerating in ways that could not be explained by gravity alone. This mysterious acceleration sparked debates that continue to this day. Was it outgassing from hidden volatiles, solar radiation pressure, acting on an unusually shaped object, or something more exotic that pushed the bounds of conventional physics, the non-detection of a gaseous coma, around? Oumuamua contradicted expectations for objects containing the typical volatile ices of comets. However, something was clearly acting on the object to produce the observed acceleration. The solution, if it can be called that, involved invoking a theory of outgassing so minimal that it remained below detection thresholds, while still generating enough force to alter Oumuamua's trajectory. 2I Borisov was discovered on August 30, 2019, by amateur astronomer Gennady Borisov in Crimea, and it presented a completely different character. Unlike its enigmatic predecessor, Borisov initially seemed comfortingly normal, a classic comet, complete with a fuzzy coma and a growing tail, whose structure matched theoretical expectations for objects heated by solar radiation. However, detailed analysis revealed that Borisov's apparent normalcy concealed a chemical composition unlike anything found in the native comets of our solar system. Spectroscopic observations showed a significantly higher concentration of carbon monoxide than is typical for local comets, suggesting formation in a protoplanetary disk with different temperatures and chemistry than our own solar nebula. The dust-to-gas ratio in the comet's coma, Borisov, also differed from solar system norms, indicating different formation processes or evolutionary changes that occurred during its interstellar journey. These subtle yet significant chemical differences provided the first direct evidence that other star systems produce comets, with compositions that reflect their unique formation environments. Now, Boii Atlas joins this exclusive club with characteristics, making both of its predecessors seem ordinary by comparison. A carbon dioxide-rich coma was detected by Spitzer and confirmed through observational studies. Next, it showed the greatest compositional difference from solar system norms ever observed in an interstellar object. The ratio of CO2 to water vapor was suggested by analysis from the James Webb Space Telescope, indicating formation conditions even stranger than those that produced Borisov. The anti-solar tail structure of 2I Atlas bears no resemblance to previously observed interstellar objects, while Oumuamua had no tail structure due to a clear lack of significant outgassing, and while Borisov displayed a conventional cometary tail, streaming away from the Sun. 2I Atlas presented a geometry that challenges the fundamental principles of cometary physics as understood through centuries of observation. A rapid, brightening trend noted in September 2025 adds another unique feature to the list of 2I Atlas's growing anomalies, as neither Oumuamua nor Borisov exhibited such sudden brightness variations over such a short period, suggesting that 2I Atlas undergoes processes, whether outgassing events, structural changes, or surface evolution, that operate on faster timescales than what is typical for previously studied interstellar objects. A comparison of sizes reveals interesting patterns within the population of interstellar visitors. Oumuamua's size was estimated at around 400 by 40 by 4 meters, significantly larger than typical small asteroids, but smaller than most active cometary nuclei. Borisov's nucleus diameter was estimated at about 1 kilometer, falling within the normal range for solar system comets. Measurements of 2I Atlas present challenges in size estimation, reflecting the uncertainty surrounding its fundamental nature. The Hubble Space Telescope indicated a nucleus diameter somewhere between 0.3 and 5.6 kilometers, a range that includes both small and moderate-sized cometary nuclei. This uncertainty arises from the difficulty in separating the nucleus from its extensive coma, which in itself is a unique feature that distinguishes 2I Atlas from its interstellar predecessors. The capability for chemical analysis evolved significantly between the detections of each interstellar object, allowing for more detailed compositional studies over time. Oumuamua's brief appearance and its lack of significant outgassing limited chemical analysis to surface reflectivity characteristics and rough density estimates. Borisov's more conventional cometary behavior allowed for the spectral detection of water vapor, carbon monoxide, and various other molecules typical of a cometary coma. 2I Atlas benefited from the most advanced observational capabilities ever applied to an interstellar object, the infrared spectroscopy of the James Webb Space Telescope, the high-resolution imaging of Hubble and ground-based observatories, equipped with new-generation spectrographs, providing unprecedented detail on its chemical composition, physical structure, and evolution over its orbital period. The orbital characteristics of each interstellar visitor also tell their own stories about galactic dynamics and the processes that eject bodies from their home star systems. Oumuamua approached the solar system from the direction of the star Vega, although its travel time exceeds the age of Vega, suggesting a more complex galactic trajectory. Its hyperbolic excess velocity, the speed it would retain after escaping gravitational influence, was measured at approximately 26 kilometers per second. Borisov's trajectory indicated an origin from a region of space containing hot, young stars in the constellation Cassiopeia, with a hyperbolic excess velocity of about 32 kilometers per second. This higher velocity suggests that it was either ejected from a more massive star system or was accelerated through gravitational interactions during its interstellar journey. Atlas carries the highest hyperbolic excess velocity ever measured for an interstellar object, calculated at about 39 kilometers per second. This extreme velocity suggests either formation around a particularly massive star or acceleration through multiple gravitational interactions during its journey through the galaxy. This velocity also influences the object's behavior near perihelion, as a higher speed reduces the available time for solar heat to penetrate deep into the nucleus. The discovery interval between interstellar visitors provides insights into their population within the galaxy. The 2-year gap between Oumuamua and Borisov, followed by a 6-year interval before the detection of 2I Atlas, suggests that these celestial Such objects regularly pass through the inner solar system, but remain difficult to detect due to their small size and brief visibility. Statistical analysis of the 3 confirmed interstellar objects suggests that each object represents a different type of small body formation process, revealing an immense diversity in how other star systems create and eject comets and asteroids, rather than converging on typical characteristics. Each new interstellar visitor has expanded the range of possible behaviors and compositions. The unique characteristics of the 3 interstellar objects, the unprecedented cometary size, the inverted tail structure, chemical composition, and brightness evolution demonstrate the diversity of interstellar bodies, including phenomena never envisioned by theoretical models based on the experience of our solar system. Each visitor teaches new lessons about planetary formation processes throughout the entire galaxy, while also raising new questions about what other kinds of interstellar objects await discovery as Comet Atlas continues its hidden journey through perihelion. Astronomers can only speculate whether this object's eventual appearance will add new entries to the growing catalog of strange interstellar objects. The pattern established by Oumuamua and Borisov suggests that Atlas will continue to surprise researchers with behaviors that challenge fundamental assumptions about the physics of small bodies. The lesson learned from all 3 interstellar visitors is that the galaxy creates small bodies through processes far more diverse and complex than those that occurred in our own solar system. Each body carries the chemical and physical signature of its formation environment, environments that are observed to be significantly different from our corner of the cosmos, providing direct samples of planetary system evolution happening across the Milky Way. Part 12. Scientific Unknowns and Heated Debates. The scientific community's reaction to the puzzle of Comet Atlas is like a detective story where crucial evidence remains hidden, forcing researchers to build theories from incomplete clues, while the most critical information lies hidden behind the sun's glare. Many competing hypotheses seek to explain this comet's unusual behavior, but each explanation raises new questions that may remain unanswered until later observations provide the missing pieces of this interstellar puzzle. The debate over size and shape. The controversy surrounding the comet nucleus's size and shape illustrates the fundamental challenges that researchers are facing. Observations from the Hubble Space Telescope have narrowed the size estimate to between 0.35 and 6 kilometers in diameter. But this wide range reflects the difficulty of separating the solid nucleus from its extensive coma. This uncertainty has significant implications, as size directly affects calculations of mass, density, and the surface area available for outgassing, and structural stability during the intense heating at perihelion. Different measurement techniques yield conflicting results. Thermal models based on infrared observations suggest a smaller nucleus with a high albedo, a reflective surface that efficiently scatters sunlight. Visible light analysis indicates a larger, darker nucleus that absorbs more solar radiation. This discrepancy could be due to variations in surface composition, measurement errors, or fundamental misunderstandings of how Comet Atlas responds to sunlight. Compositional analysis and contradictions. Compositional analysis also faces its own set of contradictions. The James Webb Space Telescope, with its clear spectroscopy, identified carbon dioxide as the primary volatile in Comet Atlas, with its CO2 abundance outstripping water vapor by a significant margin. This composition is markedly different from solar system comets, where water typically dominates the volatile components. However, the dominance of carbon dioxide creates theoretical problems in explaining other observed features. The green color that appeared in September typically indicates the emission of diatomic carbon, but the outgassing of abundant CO2 does not naturally produce the carbon-bearing molecules responsible for this green fluorescence. It is possible that the observed spectroscopic analysis missed other crucial chemical components, or that the green color is the result of more complex processes than simple molecular fluorescence. Ground-based spectroscopy from very large telescopes and other major observatories has detected additional molecular species, including cyanide compounds and various other organic molecules. These findings suggest a chemical complexity beyond the simple CO dominance indicated by space-based observations, revealing that Comet Atlas contains a diverse inventory of both simple and complex carbon compounds. The anti-tail structure, the most perplexing puzzle, is perhaps the most confounding observational enigma. Conventional cometary physics dictates that solar radiation pressure should push gas and dust away from the sun, creating tails that point in a keen, radial direction away from the sun. But Comet Atlas seems to violate this fundamental principle by ejecting material that forms sunward-pointing structures, instead of away from it. A recent theoretical analysis by Dr. Quito and Dr. Lowe, currently under peer review, proposes that the anti-tail is the result of an unusual dust particle size distribution, combined with specific ejection geometries from the nucleus surface. Their model suggests that large dust particles ejected toward the sun with sufficiently large initial velocities can overcome solar radiation pressure to create the observed forward-pointing structures. However, competing models invoke different physical mechanisms. Some researchers propose that electromagnetic effects, interactions between charged dust particles and the sun's magnetic field, could redirect material in unexpected ways. Others suggest that the comet's rotational state creates thermal asymmetries, which focus outgassing in specific directions, regardless of solar radiation pressure. The enigmatic rotation period. The rotation period of Comet Atlas remains unknown, despite months of observational attempts. Light curve analysis, which measures the changing brightness caused by an irregularly shaped body rotating in sunlight, has not revealed a clear periodic signal. This absence of a detectable rotational signature could indicate a very slow rotation, a nearly spherical shape, or a complex rotational motion that obscures simple periodic variations. Rotation affects many aspects of cometary behavior. As rapidly rotating bodies experience centrifugal forces that can affect outgassing patterns and structural stability. Slowly rotating comets develop temperature differences between their day and night sides, concentrating the release of volatiles in heated regions. The undetermined rotational properties of Comet Atlas complicate efforts to model its thermal evolution and predict its future behavior. The controversial brightness evolution. The brightness evolution recorded in September presents its own interpretive challenges. Multiple observing networks have confirmed that Comet Atlas became significantly brighter than theoretical predictions, but the magnitude of this deviation remains controversial. Some observers report a brightening equivalent to several magnitudes, while others suggest a more modest enhancement within the range of normal cometary variability. The discrepancies arise in part from measurement difficulties, as Comet Atlas remained near the detection limit of most telescopes, making precise photometry challenging, even under optimal conditions. Different observers use different comparison stars, filter systems, and data reduction procedures, which can introduce systematic errors into brightness measurements. More importantly, the lack of baseline observations complicates the analysis of brightness trends. Unlike periodic comets that have been observed over multiple apparitions, Comet Atlas represents a single opportunity target, with no historical data for comparison, investigating the galactic origin. Origin studies attempt to trace the trajectory of Comet Atlas backward through the galaxy to identify its possible birthplace. Current dynamical analyses suggest the comet originated somewhere within the Milky Way's thin disk, the star-rich, flat region where most current star formation occurs. However, uncertainties in the measured position and velocity propagate backward in time, creating ever larger error ellipses that encompass many potential source regions. The question of galactic origin has implications for understanding the composition and age of Comet Atlas. Objects ejected from young star systems may retain distinct chemical signatures, compared to those originating from older, more evolved stellar environments. The dominance of carbon dioxide could reflect formation in a protoplanetary disk with its temperature and chemical gradients differ from those that created objects in the solar system, as does its structural stability. This structural stability represents another field of intense debate. The vast tail and coma suggest vigorous outgassing, which could indicate a nucleus rich in volatile materials, or a nucleus undergoing structural disruption. Some researchers propose that Atlas represents a collection of smaller bodies, loosely bound, a rubble pile held together by weak gravity, which could break apart under the influence of thermal or tidal stress. Alternative models view Atlas as a monolithic body with unusual surface properties or internal structures, creating the observed outgassing patterns. This difference is crucial for predicting its behavior near perihelion, where thermal stress and tidal forces reach their maximum intensity. The mysterious activation point. The observed activation at 2 astronomical units in early September remains poorly understood. The sudden surge in activity as Atlas crossed this distance from the Sun may indicate the activation of specific volatile compounds that sublimate at certain temperatures. Additionally, it could reflect structural changes within the nucleus, causing previously buried volatile deposits to be exposed to solar heat. Different volatile species sublimate at varying distances from the Sun, creating a natural activation sequence as a comet approaches perihelion. Water ice begins to outgas significantly at about 3 astronomical units, while carbon dioxide can become active at much greater distances. The specific behavior of Comet Atlas suggests a complex mixture of compounds with volatile activation temperatures that do not align with our experience of solar system comets. The critical observational gap during conjunction creates additional uncertainty about which theoretical models best explain the behavior of Comet Atlas. Most importantly, the critical tests of competing hypotheses, how the comet would react to maximum solar heating, whether fragmentation would occur, how outburst patterns would evolve, were all set to happen, largely hidden from Earth-based observations. When Comet Atlas emerges from conjunction in late November, researchers will face the challenge of explaining observations of an object that may have changed dramatically during its unseen perihelion passage. This post-conjunction emergence could either confirm current theoretical models or introduce new puzzles demanding entirely different explanations. The challenge of modern science. The scientific debates surrounding Atlas reflect the broader challenge of understanding phenomena that occur only rarely and under conditions that push our observational capabilities to their limits. Every measurement has its uncertainties, every model makes assumptions, and every interpretation must account for the possibility that interstellar objects operate under physical principles not yet encountered in our solar system experience. Part 13. Natural Explanations. Before delving into the realm of speculative possibilities, science demands that we exhaust the strange, yet plausible natural explanations for this comet's perplexing behavior. A comet may be strange beyond our current understanding, but it could still be within the bounds of known physics, albeit operating under conditions so extreme they have never been observed before in human experience. The dominance of carbon dioxide, its prevalence, detected in Atlas's coma, offers the first clue to understanding its extrasolar nature through conventional cometary science. This composition suggests it formed in a region of its parent star system where temperatures were low enough for CO2 to condense into solid ice, while water existed primarily as a vapor. Such conditions typically occur beyond what astronomers call the CO2 snowline, the distance from a star where CO2 gas can freeze out of its gaseous state. In our solar system, the CO2 snowline lies much farther from the Sun than the regions where most comets are thought to form. This explains why solar system comets have water as their primary volatile component, with CO2 playing only a minor role. However, other star systems may have different temperature profiles, stellar luminosities, or chemical compositions, placing the CO2 snowline at distances where significant comet formation occurs. A star cooler than our Sun would push the carbon dioxide snowline closer to that star, allowing CO-rich comets to form in orbits similar to the regions where water-bearing bodies predominantly gathered in our own system, or a star with a different chemical composition, perhaps rich in carbon and hydrogen, could create a protoplanetary disk where the formation of carbon dioxide is favored over the formation of water ice, regardless of temperature. This formation environment hypothesis explains not only the unusual chemistry of 2I Atlas, but also its enhanced outgassing behavior, as carbon dioxide sublimates more readily than water ice at the same temperature, potentially producing gas at a superior release rate compared to predominantly water-based comets. This enhanced volatility could account for the rapid brightening observed in September and the unprecedented size of its coma detected by spectroscopic observations. However, a super CO-rich composition alone cannot explain the antisolar tail that baffled observers. Since the first detailed images emerged, this is where dusty plasma physics enters the equation, introducing processes that operate at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena as the Sun's ultraviolet radiation ionizes the gases in the surrounding cometary coma. It creates a plasma, a mixture of charged particles that responds to both gravitational and electromagnetic fields. This ionized material interacts with charged dust grains in complex ways, potentially creating self-organizing structures unlike anything predicted by simple gravitational and radiation pressure models. Charged dust particles can form filamentary flows and even helical structures when influenced by the magnetic fields carried in the solar wind under certain conditions. These electromagnetic effects can overpower radiation pressure, allowing material to flow in directions that seem to violate basic cometary physics, resulting in antisolar tail structures, while conventional tails flow away from it. The plasma physics explanation becomes more credible when considering 2I Atlas's enhanced outgassing rate. Higher gas density creates more opportunities for ionization and charge exchange, processes that can amplify electromagnetic effects. The unusual chemical composition could also influence plasma formation through molecular species that are more easily ionized or at different rates than those typical of solar system comets. The slow rotation hypothesis, its rotational state, offers another avenue to explain 2I Atlas's unusual behavior through conventional physics, applied to extreme conditions. A nucleus with a very slow rotation rate could develop significant temperature differences between its day and night sides, concentrating outgassing in specific regions rather than distributing it evenly across the surface. If the comet rotates slowly enough for its day side to reach significantly higher temperatures than a typical solar system comet, thermal expansion and gas pressure could create jets of material, ejected at velocities high enough to overcome solar radiation pressure in the sunward direction, resulting in preferential sunward eruptions from the hottest regions of the nucleus surface. The slow rotation hypothesis requires explaining why Comet Atlas would rotate differently from typical comets. Interstellar objects undergo different evolutionary processes during their journeys between star systems, such as collisions with interstellar dust particles, gravitational tugs from passing stars, or magnetic field interactions could all alter its rotational state in ways that do not occur for objects confined to a single star system. The green color and the green threshold effect that appeared in September pose their own distinct explanatory challenges. Diatomic carbon typically produces the green emission in cometary comas, but initial spectroscopic observations showed relatively little evidence of carbon-bearing molecules other than carbon dioxide. However, the threshold hypothesis suggests that the release of C2 only became significant when 2I Atlas crossed a specific temperature or solar radiation intensity threshold, near a distance of 2 astronomical units. This threshold effect could result from the photodissociation of carbon dioxide, the breakdown of CO2 molecules, by solar ultraviolet radiation into carbon monoxide and atomic oxygen. Subsequent photodissociation of carbon monoxide could then produce the carbon atoms. Carbon is essential for the formation of diatomic carbon, a process that requires specific radiation conditions and molecular densities that may not have been present during the initial observations of 2I Atlas, but developed as the comet drew closer to the Sun. Alternative carbon chemistry involves complex organic molecules, which might exist in trace amounts within the nucleus, but only produce detectable emissions under specific excitation conditions. Polycyclic aromatic hydrocarbons, amino acids, or other organic compounds could break down under intense solar radiation, producing carbon-bearing fragments that glow at blue wavelengths. Sixth, variations in surface composition offer another natural explanation for the unusual behavior of 2I Atlas. Instead of a uniform nucleus composition, the object might contain distinct regions with different chemical makeups. Some regions could be rich in carbon dioxide, others in water ice, and still others in complex organic materials. As the comet approached the Sun, and different regions on the surface experienced heating for the first time, these chemical transformations could produce time-varying outgassing patterns. The initial dominance of CO2 might reflect the earliest activation of the most volatile surface deposits, while subsequent heating could then expose subsurface materials with a different composition. Porosity and internal structure also influence cometary behavior in ways that could explain the unusual features of 2I Atlas. A highly porous nucleus is essentially a loose collection of ice and dust, held together by weak forces, which could allow for deep penetration of solar heat, activating subsurface volatile deposits that are normally insulated from external temperature changes. The enhanced porosity hypothesis explains both the extensive coma and the rapid brightness changes. Deeper heating activates larger volumes of volatile material than would typically occur in denser cometary nuclei, producing gas production rates that exceed predictions from models based on surface heating alone. Interstellar processing during 2I Atlas's journey between star systems could have induced structural changes that solar system objects do not experience. Cosmic ray bombardment, collisions with interstellar dust, or thermal cycling during passage through different radiation environments could all alter the nucleus's properties in ways that affect its behavior. When the object finally encounters intense stellar radiation, most likely, the unusual behavior of comet 2I Atlas is explained by a combination of these natural processes occurring simultaneously. A CO2-rich composition drives enhanced outgassing. Plasma physics creates the anti-tail structures. Slow rotation concentrates activity in specific regions, and complex chemistry produces the observed color changes, while each individual process remains within the realm of well-understood physics. Their interaction under the extreme conditions of an interstellar cometary event can produce phenomena that seem impossible when viewed through the lens of solar system cometary experience. 2I Atlas may represent a profoundly strange comet, rather than something fundamentally alien, but that strangeness makes it precisely the kind of object that could revolutionize our understanding of the physics of small bodies throughout the galaxy. Section 14. Exotic and Fringe Theories. We now enter the territory where science fiction meets speculative possibility, where the boundary between natural phenomena and truly extraordinary explanations begins to blur. Although no credible evidence supports these interpretations of Comet 2I Atlas's behavior, yet its unprecedented features invite the kind of speculation that every unexplained astronomical phenomenon throughout human history has encountered. These ideas exist not as serious scientific hypotheses, but as thought experiments that illuminate just how strange our interstellar visitor truly is. The alien technosignature hypothesis is perhaps the most persistent exotic explanation for unusual astronomical objects. Ever since the discovery of Oumuamua sparked debates about an artificial origin, each new interstellar visitor has inevitably generated speculation about possible technosignatures. 2I Atlas's rapid brightening, its unusual anti-tail structure, and its enhanced coma could, in theory, represent the activation of some form of probe, some kind of automated probe designed to react to the stellar radiation environment. The beacon scenario envisions Atlas as a dormant technological artifact, remaining inactive throughout its long journey between star systems, preserving its power and structural integrity until it encounters conditions that trigger its pre-programmed procedures. The brightening event in September could mark the moment when solar radiation reached sufficient intensity to power its dormant systems, while the anti-tail structure might represent a directional emission of energy or ejected material, serving some technological purpose. However, this technological interpretation faces immediate challenges when confronted with observational evidence, with spectral signatures detected by the James Webb Space Telescope, and ground-based observatories showing clear evidence of standard volatile compounds, carbon dioxide, water vapor, and organic molecules, consistent with the expectations for a comet's natural outgassing. No unusual isotopic ratios or artificial materials were detected, or the characteristic energy signatures of advanced technology. The quasi-living plasma hypothesis delves even deeper into the realm of speculation, based on research into complex plasma behaviors that can exhibit seemingly organized patterns under specific conditions. Laboratory experiments have demonstrated that dusty plasma, a mixture of charged particles and microscopic solid grains, can self-organize into structures that display properties reminiscent of biological systems. These plasma formations can replicate, evolve, and respond to environmental changes in ways that superficially resemble living organisms. Some researchers have suggested that such complex plasma systems could arise naturally in space environments, potentially developing behaviors that mimic primitive life. The anomalies of BY Atlas, its outgassing patterns, the anti-tail structure, and its reactive brightening, could, in theory, represent the manifestation of such plasma-based phenomena. The living plasma concept suggests that interstellar space might harbor forms of organization that operate on physical principles entirely different from carbon-based biology. These hypothetical entities could exist in a dormant state during interstellar travel, but become active upon exposure to the electromagnetic environment around stars, producing observable effects that mimic, but do not actually represent, biological processes. However, this explanation requires invoking physical mechanisms that remain purely theoretical. For while dusty plasmae can indeed form complex structures under laboratory conditions, Extending these phenomena to comet-sized objects, operating in the solar wind requires extrapolations that go far beyond current scientific understanding. No observational evidence suggests that BY Atlas exhibits the kind of electromagnetic signature expected from a large-scale plasma organization. The purposeful probe narrative casts BY Atlas as an active reconnaissance mission from another star system, complete with programmed behaviors to study our solar system as it passes through the inner regions. This scenario envisions the comet's unusual features as intentional functionalities. The vast coma could provide sensory or communication coverage, while the anti-tail structure might represent a data transmission system aimed at distant receivers. The probe hypothesis suggests that the brightening of BY Atlas was not random outgassing, but a controlled activation of observational and communication systems as the object approached its primary mission targets. The timing of peak activity near Mars and during perihelion could reflect predetermined survey protocols, rather than mere reactions to solar heat. This interpretation leads to romantic speculations about BY Atlas waking up as it encountered the characteristic signatures of our star system. Its artificial consciousness awakening after millions of years of dormant interstellar travel. The brightening could mark the moment. Dormant sensors came online, while rapid brightness changes might indicate data processing and transmission activities. However, this reconnaissance scenario also faces the same evidentiary challenges as the technological beacon hypothesis. The chemical signatures, the thermal properties, and the structural characteristics of BAI Atlas are consistent with expectations for natural objects, albeit unusual ones. There is no evidence suggesting information processing, directed communication, or other activities characteristic of technological systems. The strange matter hypothesis suggests that BAI Atlas contains material or operates according to physical principles unknown to current science. Theoretical physics suggests the possibility of exotic forms of matter with unusual properties, interactions with dark matter, modified gravitational behavior, or quantum effects operating on a macroscopic scale, which could produce observable phenomena distinct from standard physics. Strange matter could explain the unusual anti-tail of BAI Atlas through gravitational anomalies that deflect the flow of material, or account for its enhanced outgassing through energy release mechanisms that go beyond conventional chemistry. The rapid brightening could reflect exotic phase transitions, or energy storage systems operating under an undiscovered physical law. This interpretation allows for natural phenomena that still exceed current scientific understanding, suggesting that BAI Atlas is not artificial technology but rather natural processes involving physics that human science has not yet encountered. This object could serve as an accidental laboratory for studying physical principles that do not manifest under the typical conditions of Earth-based research. Speculation about temporal anomalies enters the most exotic territory, suggesting that BAI Atlas could represent a form of information or matter transfer across cosmic timescales. Science fiction imagines the comet as a message or artifact from our future sent back into the past, using technologies that bypass conventional causal limits. This interpretation views the anomalous properties of the celestial body, BAI Atlas, as evidence of temporal manipulation rather than interstellar space travel. The object might originate from a future version of our own solar system, carrying information or materials intended for our current era. Its strange behavior could reflect the interaction between future technology and present physical conditions. However, time manipulation scenarios require physics that is not only unproven, but also contradicts fundamental principles of causality and thermodynamics as we currently understand them. There is no observational evidence that BAI Atlas violates conservation laws or exhibits temporal anomalies beyond the standard relativistic effects expected for high-velocity objects. From a critical perspective, all these exotic explanations highlight that seemingly mysterious astronomical phenomena often receive mundane explanations once sufficient data is available. The initial discovery of pulsars generated speculation about artificial signals from advanced civilizations. But these objects turned out to be neutron stars, spinning rapidly. Fast radio bursts sparked similar debates before being traced to natural astrophysical processes. History suggests that BAI Atlas will eventually find an explanation within known physics, though it may involve processes or conditions not previously observed. The comet's unusual characteristics may reflect the vast diversity of conditions present in other star systems, rather than a manifestation of exotic physics or artificial technology. The value of exploring these speculative scenarios lies not in their probability, but in their ability to highlight just how extraordinary BAI Atlas truly is in the context of human astronomical experience, an object that can seriously inspire considerations of alien technology, living plasma. And strange matter represents something truly unprecedented in our understanding of interstellar visitors, as BAI Atlas continues its journey toward perihelion. These exotic explanations remind us of how much we still do not understand about the universe beyond our solar system. In any case, whether the comet emerges from its solar conjunction as a perfectly normal, if unusual, object, or continues to display characteristics that defy conventional explanations, it has already succeeded in pushing the boundaries of what we consider possible for visitors from other star systems. Part 15. Countdown and Consequences. The cosmic clock is counting down to a series of moments that will determine not only what BAI Atlas reveals about itself, but also what it teaches us about the wider interstellar population of the larger interstellar wandering objects. Each upcoming milestone represents a significant challenge to our understanding, our observational capabilities, and our ability to extract meaningful scientific discoveries from phenomena that push the boundaries of current astronomical practice. October 3rd, 2025 marks the first critical turning point as BAI Atlas makes its closest approach to Mars, at a distance of about 30 million kilometers. This encounter offers the best opportunity for humanity to maintain surveillance on this interstellar visitor during the period when Earth-based telescopes begin to lose sight of it. The mechanical eyes orbiting Mars will attempt observations never intended by their original missions, pushing technological limits to capture images and spectra of an object hurtling past at interstellar velocity, with success depending on variables beyond human control. If BAI Atlas maintains or increases its current brightness, the Mars orbiters might capture detailed images of the nuclear structure and the dynamics of the cometary tail that are invisible to Earth-based telescopes. However, if the comet fades from its September peak, even the most sensitive spacecraft instruments may only detect faint signals, insufficient for meaningful scientific analysis. Late October brings the hidden perihelion from the 29th of October to the 30th, at about 1.36 astronomical units from the Sun. During these critical days, BAI Atlas will experience radiation intensities that could trigger its most dramatic transformations of its entire solar system approach. The peak temperatures could activate volatile compounds that remain stable throughout the comet's interstellar journey, potentially producing spectacular outgassing events sufficient to alter the object's fundamental properties. However, perihelion occurs almost exactly when the comet becomes most difficult to observe from Earth, obscured in the sun's glare that no ground-based telescope can penetrate. A cosmic irony places the moment of maximum scientific interest precisely when human observational capabilities are at their minimum. Any discoveries that perihelion yields will remain largely hidden from direct observation, surviving only in whatever indirect evidence remains for later analysis. The observational gap extends until early November, creating a 4 to 5 week period when Biatlas effectively disappears from human scrutiny. This forced silence occurs during the phase that theoretical models predict will be the comet's most active stage, potentially including fragmentation events, significant brightness changes, or chemical transformations that would normally trigger intensive observation campaigns. The re-emergence in early December represents the next crucial milestone, when the solar elongation increases enough for Earth-based telescopes to locate and track Biatlas after its hidden journey. The comet that emerges from conjunction may not resemble the object that disappeared in October, possibly showing signs of fragmentation, dramatic changes in brightness or composition, and evolved chemistry, reflecting its interaction with intense solar heat. Post-perihelion scientific opportunities in the following year and beyond. The Jupiter approach in March of 2026, although occurring at a much greater distance than the encounter with Mars, could offer additional spacecraft observation opportunities as Biatlas begins its final departure from our solar system. The geometry might permit remote observation by missions like Juno or the upcoming Europa Clipper, depending on their operational status and orbital configurations. What we can learn from successful observations extends far beyond the specific characteristics of Biatlas itself, as interstellar chemical analysis provides direct samples of material that formed around other stars, preserving information about the chemical conditions present in protoplanetary disks throughout the galaxy. The detected carbon dioxide-rich composition suggests formation environments different from our local solar nebula, indicating that the chemistry of planetary systems varies much more widely than previously imagined. Studying the comet's behavior under extreme conditions can refine outgassing mechanisms, dust particle dynamics, and plasma physics in extraterrestrial environments. The anti-tail phenomenon challenges fundamental assumptions about how materials from a comet responds to solar radiation, potentially requiring new theoretical frameworks to account for electromagnetic effects not considered in conventional models. Broader scientific significance, extending to wider questions about interstellar objects and their role in chemical evolution throughout the galaxy. 3I Atlas represents only the third confirmed visitor from another star system, but its unusual characteristics suggest that the galaxy contains a much greater diversity in the formation of small bodies than current theories predict. Each interstellar object studied provides crucial data points for understanding how common these visitors are, and what they reveal about conditions in distant star systems. Fragmentation analysis. If 3I Atlas breaks apart during perihelion, could offer unprecedented insights into the internal structure and compositional gradients of an interstellar object. Different fragments may contain material from various depths within the original nucleus, effectively providing a core sample of an object that formed around another star. The dispersal of fragments and their chemical differences could reveal structural details, impossible to determine from observations of the intact object. Managing expectations requires acknowledging the inherent limitations of studying objects that remain at the threshold of detectability, even under optimal conditions. 3I Atlas will likely never become a naked-eye spectacle for observers on Earth, with peak brightness estimates hovering around magnitude 11 to 12, which is within the reach of telescopes, but invisible without optical aid. The lack of a dramatic visual display does not diminish its scientific value, but it does limit opportunities for public engagement, which often drives continued funding and interest in astronomical research. The European Space Agency's future Comet Interceptor mission, scheduled for launch in the late 2020s, is an effort to develop a rapid response capability to study newly discovered interstellar objects. Unlike traditional spacecraft missions that require years of planning for specific targets, Comet Interceptor will wait in space at a Lagrange point of the Earth and Sun until a suitable target appears, at which point it will redirect to intercept and study the object as it passes through the solar system. However, the capabilities of Comet Interceptor are still limited by the fundamental challenge of detecting interstellar objects early enough to allow for spacecraft intercept missions. 3I Atlas was only discovered a few months before its closest approach to the Sun, providing insufficient lead time for dedicated spacecraft missions. Even with such rapid response capabilities, future detection systems must identify interstellar visitors years in advance for meaningful spacecraft encounters to be possible. Improvements in ground-based surveys offer the promise of advancing interstellar object science. The Vera C. Rubin Observatory, currently under construction in Chile, will begin operations in the mid-2020s, with an unprecedented ability to survey the sky. Its capacity to repeatedly image large sections of the sky could identify interstellar objects much earlier in their passage through the solar system, providing extended observation windows and better opportunities for detailed study. The Legacy Survey of Space and Time, the primary mission of the Rubin Observatory, is expected to discover interstellar objects at a rate of several per year once full operations begin. This significant increase in detection frequency will transform interstellar object studies from rare, opportunistic observations into systematic population studies, which could address fundamental questions about the galaxy's reservoirs of small bodies and their chemical evolution. Technological developments in adaptive optics, spectroscopy, and space-based observation continue to push the boundaries of what can be learned from faint, fast-moving targets like 3I Atlas. The next generation of extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope, will provide light-gathering power and spatial resolution that could revolutionize the characterization of interstellar objects. The infrared capabilities of the James Webb Space Telescope have already proven their value for interstellar object studies, providing chemical composition data that was unattainable with previous instruments. Future space-based observatories optimized for the study of small celestial bodies could provide continuous monitoring, unhindered by the limitations of Earth's atmosphere or periods of solar conjunction. International collaboration is increasingly vital for the study of interstellar objects. It requires coordinated observations across multiple facilities and time zones. The BA Atlas observation campaign has demonstrated both the potential and the challenges of organizing a global response to rapidly evolving astronomical targets. The lessons learned from this coordinated effort will inform future responses to similar discoveries. The data sharing and analysis protocols developed for the BA Atlas observations are setting standards for the astronomical community for handling rapidly changing, high-priority targets that demand immediate responses from multiple observatories. These procedures will prove essential as the detection rate of interstellar objects increases and coordinated research opportunities become more frequent. The broader implications extend beyond astronomy to fundamental questions about the nature of matter and chemistry throughout the galaxy. BA Atlas provides direct physical evidence of the conditions in other star systems, preserved in a pristine state over millions of years of interstellar travel. Each measurement contributes to understanding how the processes of formation of planets vary between different stellar environments. Astrobiology considers the factors arising from the study of interstellar objects, as these visitors could transport organic compounds or even primitive life forms between star systems. Although there is no evidence that BA Atlas contains biological material, its organic chemistry could provide insights into the distribution of complex carbon compounds in the galaxy. The discovery of amino acids, nucleic acid bases, or other prebiotic compounds in interstellar objects would have profound implications for understanding how the chemical building blocks of life spread through space. The unusual chemistry of BA Atlas, though not directly biological, suggests that interstellar objects can preserve complex molecular structures over galactic distances. Planetary defense considerations, though not relevant to BA Atlas due to its safe trajectory, benefit from studies of interstellar objects, which improve understanding of how such objects behave under the influence of solar heating. Interstellar visitors in the future could follow trajectories that bring them closer to Earth, requiring accurate predictions of their behavior to assess collision risks. The unusual characteristics of BA Atlas reveal limitations in current models used to predict cometary behavior, suggesting that planetary defense systems must account for types of objects that do not match our solar system experience. An enhanced understanding of interstellar object physics could prove crucial for accurately assessing the risk from future visitors that might pose a real threat. Public engagement opportunities surrounding BA Atlas reflect both the challenges and rewards of communicating cutting-edge science to a general audience. The technical complexity and the comet's faintness create barriers to casual public interest. However, its interstellar origin and unusual behavior generate excitement among those who grasp its significance. Educational institutions worldwide are integrating observations of BA Atlas into classroom activities, using the comet as a real-time example of scientific discovery and progress. Students can follow the observation campaigns, analyze public data, and witness the evolution of scientific understanding as new evidence emerges. The commercial space industry shows growing interest in studies of small bodies, recognizing both the scientific value and economic potential in characterizing asteroids and comets. Although BA Atlas offers no mining or resource opportunities due to its hyperbolic trajectory, the techniques developed to study it contribute to broader capabilities for characterizing small bodies that could prove commercially valuable. As we approach the critical days of October, BA Atlas has already succeeded in demonstrating that interstellar visitors will continuously challenge our assumptions about what is possible in the cosmos, beyond our solar system. Will the comet's future behavior confirm theories, or introduce entirely new mysteries? It has set a new standard for surprises in astronomical phenomena, the final capstone that will define the legacy of Atlas, depending on observations revealed in the coming weeks, as it begins to reveal what it truly is. A chemical time capsule from another star, a physics laboratory operating under conditions never before observed, or perhaps something even more extraordinary, forcing us to rewrite our understanding of what wanders between the stars. In the coming weeks, it will either flare up with unprecedented brightness, shatter into a chain of interstellar fragments, or silently glide past our sun, carrying its secrets back into the cosmic darkness. And whatever happens, it could fundamentally change how we think about visitors from other suns. The call to action for anyone able to follow this cosmic detective story is clear. Follow the mission image releases from ESA's Mars Express and Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter and MAVEN, and then wait for updates after perihelion from the Hubble and James Webb Space Telescopes, which may finally reveal the true meaning of Atlas. The universe has sent us a messenger from another star, and we are about to learn the message it carries.